Okay. Okay. So first we will start from your query. If you have any query related to any question from week 5 to week 8.
Sir, the mock for quiz 2, question 5.
Okay. Okay. Sure. Yeah. We will discuss the
Closest
mock
pair,
also. So
sir. Closest pair and sir,
yeah,
counting version, sir.
closest pair,
AVL tree.
ABL tree. Okay. So any particular question from the mock 2?
Sir, last
Sir, why
session,
none assignment has deadline but mock question has deadline, sir? We forgot, sir. None means even a quiz one mock there is no deadline.
Yeah, so this time actually we also want to check that how many of you are submitting this mock 2, and what you are actually, what score you are getting.
Sir, but
Sir, actually, we did
we
not check
forgot,
for the
sir.
deadline. Yes, sir, we missed the.
So still you have questions, so similar to the practice assignment, don't see the answer and directly try to solve the
Okay,
question first, then
that
you
we
will see
have
the
done,
answer.
but then we cannot, like, you won't know that we have done it, right?
Hmm. So that means you missed to submit that mock 2.
Sir, we missed to submit, but like we solved it later, like hiding the answers and trying to solve it ourselves.
Okay, okay.
usually it is on the quiz day, but yeah, this time it's a little bit, I mean, like Sunday or whatever, the day before the quiz for the
Not
mock.
usually. I need diploma. There is no deadline for mock.
Yeah, so in the previous terms or previous time, actually we release as a practice assignment, so there is no deadline, and you can click
Even
on the
in
answer.
DBMS, that is the case.
Okay, bye bye bonus marks.
Hmm. Okay. So, but the mock is released, I think, on maybe Monday this time. But still, we have set this deadline on Thursday, 4 days. You should submit before the deadline. And we have also sent the announcement regarding this. Okay, so first thing, the questions from the mock. So just tell me which question you are facing difficulty in mock.
AVL tree, sir, AVL tree.
Okay, I'm opening the mock and I'll come from the starting. Just tell me which question you have difficulty from the starting. And last session, can anyone tell me which part is completed? Week 6 is complete.
Yes, sir. Last session, 5 and 6 was completed by Bhaskar sir. So this time, I think
Okay, so
you're
week
saying
7
that
and week 8 we will
8
discuss
should
today.
be discussed today. That was so. If you can maybe ask all the students what are the concepts, difficult concepts that like to cover, so you can do that, and then after that, of course,
Yeah,
it
weeks
can be.
definitely we will discuss week 7 and 8 questions and topic. Okay. So yeah, so first question, just tell me the question sequence number if anyone have any doubt.
Sir, question 5.
Question 5. So before 5, anyone have any query? Okay, so this question. Okay, one second. Okay, so here actually the information, some information is given. Like we have one four vertex, okay, in the graph, and this graph we can take any. So A like A, B, C, and D. Okay, here it is mentioned that there are six edges which are connecting all these vertex, and the weights of these six edges are 3, 4, 5, 6, 7, 8. Okay, so here we are finding out that maximum possible total weight. Okay, so maximum possible total weight that a minimum is weight spanning tree of G can have. Okay, so there are multiple way we can assign these weights on the graph on the edge. So we can simply connect like these six edges in that way. Okay, so this six is okay. So all six edges is required. Yeah, fine. So this is actually complete graph. Yeah, so we can assign these weights in any order in the edge. Okay, so suppose if I am assigning like 3, 4, 5, 5, 6, 7, 8. Okay, so there are multiple way to assign these weights on the edge. But what are the possible minimum spanning tree which we can achieve from different possible graph? Okay, so first thing is that in the all possible case of graph, you will always choose the minimum weight edge first to create a spanning tree. Definitely. Okay, so B, C, and D. I am creating a minimum spanning tree. Suppose we are using the Kruskal algorithms. Okay, so according to the Kruskal algorithms, we always select the minimum weight edge first. Okay, so suppose we are selecting minimum edge in the from the graph, so definitely you will select 3, this 3 one. Okay, so we are selecting this 3. So during the first edge selection, so one edge cannot create a cycle. So if this 3 weight edge is coming at any place in this any edge, okay, so definitely it will select first. So there is no problem to select this edge in our minimum spanning tree. Same things for the second edge. If we are selecting second edge, so suppose this, in the current graph, this is the second minimum weight edge. So we are selecting this one. Still, you this edge also cannot be eliminated because in two edges you cannot create a cycle. Okay, in two smallest edge. So if this 4 is as coming at any place, okay, in this graph, original graph, so it will not create a cycle when we are selecting only two edge. So this edge will also select in the minimum spanning tree. Okay, but for the third edge, okay, so when we are selecting third edge, so in the original case, this third edge is at this place. Okay, so we can select this because this is not creating a cycle. In in three edge, okay, so definitely in third edge maybe create a cycle in
Okay,
our
so
minimum spanning tree.
minimum weight will be 12, right?
Yeah, so this is the one possible minimum spanning tree where we are getting 12 weight. Okay, but here in the question we are asking that maximum possible total weight. So suppose the another situation, if this 5 weight is assigned to in between these 3 and 4 edge in the cycle of this. Okay, so this 5. Okay, and this is 7, like, then you cannot select this 5 as a third edge in your minimum spanning tree. So A, B, C. Okay, so you definitely you will select this 3 from here, 4 from here, but then you cannot select this 5 because it will create a cycle. So at the time you have to skip this and you have to choose next edge, and this is now this one 6. Okay, now you are getting 30. So there are two possibility in this case where either you can get 12 or you can get 30. There is no other possibility other than these two. So for the minimum spanning,
Sir, excuse me, sir.
yes,
Uh, we have selected 3, 4, and we have keep it constant, and then 7 and 8 can also be inserted in that same way.
no, we are creating a minimum spanning tree.
I mean, it will also create minimum spanning tree.
So how you can select 7? Just give me some graph idea where
I mean,
in this
in
case you can
place of
select 7.
6, can we
Okay,
write
I'm
7
creating
or 8?
B, C, D. Just
It will
I'm
violate voxel.
just tell me
Okay,
which edge I should assign which weight.
like AB being 3, AC being 4, and BD being 7.
BD 7.
Yeah.
Okay, then other.
and AC and AB being originally 3 and 4.
1 second. Sorry, AD is
3
3.
AC. Sorry,
No,
AD
uh,
no, sir. AB, AC, and BD. Will it not create a spanning tree?
no others. Then you have to put other weights also, na, in the original graph. So you are
Okay.
given six edge weights: 3, 4, 5, 6, 7, 8. Okay, you have filled 3, 4, and 7, but you have also filled 5, 7, 8, 8 on the other edge.
Okay.
Okay, suppose if you fill this 5 here, or 5 on any like this edge, okay, and 7, 8 on this edge, and 6 on this edge. So initially, still you will select first this 3 AB. Okay, 3. Then you will select 4. Then you will select next smaller weight. So you will select 5. So 5 is not creating cycle. Okay. So now this is a spanning tree. But here you are getting 12. This is the minimum possible situation. Okay. So you can create any graph, you can create any situation. You will always get two possibility where you are getting either 12 or either 30. You cannot pick bigger. This 7 and 8 will definitely not select in the any spanning tree.
Okay, we will get only two answers.
So you,
It's
there,
most
yeah, there are
minimum
two
and then
possible
next.
situation are there, and out of these two, maximum is 30.
Okay, sir.
Okay. Yeah.
So essentially, the way to think about is to basically to find the MST.
Hmm.
You need three edges because there are four vertices, right?
Yes, definitely.
So that means when we are doing any kind of algorithm, the
Hmm.
smallest number and the second smallest number will always be there,
Yes.
right? That's one way to
Correct.
look at it, right?
Correct.
Then really what happens is then there are two cases. Obviously, the solution will be involved smallest, second smallest, and third smallest number. But then there
Hmm.
is another possibility where
Hmm.
the smallest, second smallest, and the fourth smallest number will be there in the solution.
Yes,
So
when
this
third smallest is creating a cycle.
correct. Now, if
Yes.
we change the problem from 4h to 5h and with other numbers, then of course the same principle will also apply, right? So,
Yes. Yes.
so
Correct.
now we have instead of two choices,
The choice will increase in
yeah.
that case.
Can we discuss that? Because I think quiz will have similar questions.
Yeah. So you have to think more. So because of that, actually, if we give more vertex, the choice will also increase, and you have to think more about in that case. So A, like B, C, and D, and E. Because in this case, if we are creating a graph, so first thing we need many number of ways, like sorry, 5 into 6. Sorry, yeah, sorry, 5 into 4 divided by 2. 2.
So here the number
Okay.
of edges were 1.5 times the, so
Yeah,
what do you call it?
total, if we create a complete graph, so total 10 edges are possible now.
Yeah,
Okay, in this case, so we have to connect like this in the all. Okay,
that's
now.
it. Yeah.
Okay, so now we have total 5 vertex, and in 5 vertex, we need 4 edge.
And I have 9 edges total.
For MST.
10,
So
10, 10.
C and E we
C
missed.
and E,
C and
C
E.
and E.
Oh, one is missing. Okay, C. Yeah. Correct. Okay, so total 5 vertex, 4 edges required in the minimum spanning tree. Suppose if I'm taking the weights like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1 and 2 definitely will not create a problem. It will definitely select. Okay, but for third, then from third we have to think it maybe create a cycle or not, like this situation. So one,
Sir, I think second greatest number will come in third, right?
One second. So 1 and 2 we are definitely select. We can select. Okay, so because 2 edge will not create a cycle, but third maybe create the cycle in between. So like this is 1 and this is 2. So C and B.
Sir, if it
This.
is totally disconnected, why 1 and 2 will be selected? Suppose AC is 1 and BE or BE is 2.
Hmm. Yeah,
So
that
why
is
do
also possible. But we are just thinking for the
No,
maximum
no. The
case.
question would be a simple connected graph only.
yeah,
If
but
it is unconnected, we cannot find out any minimum spanning tree and all, right? We
no, it's
cannot
a
connect.
This
Minimum
kind of
spanning tree is
question won't
applicable
come,
only
right?
for.
Because this is increasing the complexity a bit too much.
Yes.
Yeah.
So because of that,
So
this question is given only for 4 vertex, where the only 2 possibility are there. I think that that possibility can be figured out.
Because 1 hour only for the paper, right?
yeah, yeah. So only thing is, if such a question comes, it will not be fully connected graph. It will be kind of connected but not fully connected. So some of the edges will be there. So that way it will be 3 or 4 combinations.
no.
That
What I'm telling, it's a connected graph with the weight AC is 1 and BE is 2 and AB is some 4.
Hmm.
So
So here we are not talking about any particular situation. We are finding out the situation where we are getting maximum possible spanning tree. Wait.
let's move on. Thank you.
So yeah. So 1 and 2. If 1 and 2 weights are coming at any place, definitely we will select. We can select in the MST. It will not create any problem. So this one weight and 2 weight edge will not create a cycle. So it can definitely select. So if I create 1 second, so like A, B, C, D, E. So this AB and AC. Suppose I am selecting this like 1 and 2. If we are selecting 3, so this 3 maybe connect this B and C. So this can be skipped.
yeah. So we have to find
Okay.
the whatever create cycle. We have to skip and let's give it a minimum weight
Huh.
available. Yes, right.
Yeah. So here actually 4, if this 3 is creating a cycle, then 1 second. Okay, if 3 is here, we will select 4. Yeah, suppose 3 is creating a cycle, so we will skip that. Then we will select 4. Okay, but after that 4, so we are selecting this 1, this 2, then we are skipping 3, then we are selecting 4 from any place.
Sir,
So
just
4.
one thing. If we have to find the maximum of the minimal spanning tree, we can do is whatever small things we are encountering after 1 and 2, we can just put them in the cycle wala positions. है ना? We can place them such, and then we skip them, and then whatever is left is going to make that maximum thing, right?
Yes, here we want to select the maximum weights that are possible actually. So we just ignore this 3 here because it can create a cycle. Then we can select the fourth next weight, 4. Okay, but now for the 5. So suppose in this case we have to check this.
Sir, here
So
A and E are
5 can
connected.
create a cycle
Sir,
with 2 and 4, right?
I think 5 and 6 both can create sir cycle.
Yeah,
hmm,
because AE
So
and
we can
C.
skip 5 and 6.
yes, yeah, there are multiple possibility are coming
BC
at
also.
when at the 5 or 6 place. Suppose
So even
5
BC
and
also.
So
So
suppose 5 is connected at this place. Okay, so it cannot select. Okay, and suppose 6 is connecting like this. Okay, so it can also not create a cycle. So we have already skipped this part, this B and C with 3 edge. But after that, how many possibility are there to create a cycle? Only E to A and E to C. 2 possibility are there. So
yeah,
we can assign two smallest weight on that, 5 and 6. That means we can skip 5 and 6 for the next edge, which may be create a cycle. But after that, we can select 7. So after ignoring these two, the next one will not create a cycle.
So
Any
7
edge.
plus 4 plus 2 plus 1. That's the answer.
Yes. So 1 plus 2 plus 4 plus 7.
Awesome. Thank you,
Okay.
sir.
Yeah, this will the case. Okay. Any any question on mock?
So, sir, I think this will make a
Question
pattern that
question
first we
6.
have to leave one, then we have to leave two, then we have to leave three. Is that so? So that we can solve any n number of graph.
Leave
Like,
means you
firstly,
cannot
we
leave.
missed.
You cannot leave 1 and 2.
No, I'm saying that firstly we leave three, only one edge. After connecting
Ah,
another edge, we leave four and five, two. So
yes.
can we think that corresponding we have to leave next wave we leave leaving three? Is that the case?
No, in this case, this is the possibility. So we want to ignore the smallest weight edge. So we will put this smallest. So 1 and 2, definitely it cannot create a cycle. So we cannot ignore this. So what we can ignore? So from third edge, we can check, we can ignore something. So from, because third edge can create a cycle in the graph. Okay, so you can find out the cycle using 3 edge in the graph. So we can ignore 1 from B to C. Then we can assign the smallest edge weight on that 3. Okay, so there is one possibility when we are selecting on these 3 edge. So this is the first possibility when we are getting. So here we are ignoring 3. But next, so after ignoring this, we will select next weight. We can select next weight. So if we suppose if this 3 is at this place, so if 4 is coming at any place, so that will not create a cycle, because the situation of this time there is only one situation which is creating a cycle is 3. Okay, so if we have ignored this, so definitely 4 will select.
Sir, we'll also add up 8, right?
Where?
In the 1 plus 2 plus 4 plus 7 plus 8, right?
No, we have 5 vertex, so we need only
Oh,
4
okay,
edge.
okay, fine.
No, sir. My question was that if we are asked for any n vertices graph, not this five. So the pattern which we can see that after 1, 2, we skipped one vertex, that is 3. So in the ascending order, every time we can leave, firstly we will leave only one vertex, that is 3. After that, we leave 5 and 6. We selected 7. So after that, we can skip 8, 9, 10 and select 11. So that will never form a cycle. Is that we can think for any n number of case which is asked?
Yeah,
I'm not
that
asking
things.
about
Yeah,
this.
that things we have to check that. So after selecting 6, so how many possibility are there to creating a cycle? So suppose if we make one more, so like D, E, F. Okay, we are connecting F. So
So,
hmm.
so the statement he made is applicable if it is a fully connected graph.
Yeah, I'm asking for fully connected graph only. Only in
Yes.
that case we can
That is
draw.
okay.
Otherwise, we cannot draw. That is not a case. We cannot draw otherwise.
Yeah, that I'm just checking that. So the what actually pattern we are getting to ignore the edge. Okay, so after selecting the next vertex, actually, if we are selecting this, so here 5 and 6 we are ignoring. So we will select next 8, 7. Okay, so suppose 7 is connecting. So 7 maybe connect. Yeah, there is multiple way to connect. So suppose this DE. Okay, so if we are connecting 7 at this place, so what are the possibility of edge to create a cycle now? So DC one, there is one possibility DC, and DB
DC,
and
AD,
DA.
and BD. Yes, sir.
Yeah, so yes, correct. DC and DA and DB. 3 edge, yeah, yes, correct. So 3 edge we can skip, or any other
No, sir.
skip.
So I think
Yeah.
this is making a pattern. For 6, it is
Yes.
making a pattern.
So initially from third, okay, so we can skip third. Then after taking 1, we can skip 5 and 6. Then after 1, then we 8, 9, 10, like this. So we have to check this further. So are we getting the same
So,
pattern?
so basically, it's like if you have created a visitor dictionary, we're keeping all the nodes we are visiting, right? So we are visiting. So essentially, we're traversing through that edge. Once we have visited, you cannot draw an edge to a visited nodes. So that is the elimination. So the number of elements you eliminate, it will take the smallest possible value. So with that logic, we can actually, when you're traversing 1 to I, when I'm in ith vertex, I cannot connect to any of the I minus 1 vertices I've already visited. That means I minus 1 smallest values at that point in time have to be ignored. So that is kind of the algorithm to kind of on a fully connected graph. But if it is not fully connected, then obviously, and the values are not distinct, then everything will go for a toss.
Yeah, correct.
Yeah.
Okay, so you can also explore this. So after
Sir,
taking some more
question 6 from mock.
vertex, just to the pattern. Yeah, I'm coming on that. Okay. Question 6. So consider a binary tree B 20 nodes. The number of nodes 2 child. Yeah, okay, fine. So here actually some information is given. 20 nodes are given in the tree. Okay. So 20 nodes are given. So how many edge are possible?
19.
19. So definitely in the binary tree. So one less than of the number of nodes are edge possible. So, okay. So 19 edge are possible. So we are getting this information. And then after that, this information is given. So that two child nodes. Okay. That means nodes which have two child. So that are actually 7. So that means node which have two child. Okay. So this is considering as a two child node. So you can see if any node have two child, that means two edge are connected below that node. Okay. So that means two edge are connected 1 and 2 below that node. So if you have 7 this type of nodes, so how many edge are connected below that? So 7 into 2,
14.
14. Okay, so that means these two child nodes are connected with 7 edge below. Okay, so that means we can just subtract this from 19. So we are getting now 5. So that means 5 edge are also remaining. So these 5 edge is actually creating by the node which have only one child. Okay, so if any node have one child, so that is actually creating a one edge. Okay, so like this. So here you can see this edge is have only one child. This is also have only one child. So all are actually creating a one edge below. So that means this 5 and the leaf node. So leaf node is actually not connecting with any edge below the node. Okay, so that is there is no child. So here actually this 5 value is representing the nodes which have only one child. So this is the simple answer for this. So 5 is the answer for this.
I hope we get a question like this, sir.
Sir,
Okay.
then where will the no child nodes go?
Sorry?
Where will we consider the no child nodes? Means those
That are leaf
base
node actually.
leaf nodes. So
Huh.
they will be covered
So,
in both these child classes.
Suppose I'm taking one example. Okay, let's see.
So I did it in a different way. Like because 20 nodes are there, so log 20 would give you the levels.
Log 20.
Yeah, so because log 20 to the base 2. So you get like around the 4 levels and then the 5th level. So those 4.
Oh, so
So
that is
like
actually
yeah, it'll be like 7 would be there, and then
But we
below
cannot
7
guarantee
would be
that,
there.
right? This is not a binary search tree. This is just a binary tree, and we
Yeah,
cannot
but
assure
binary,
that
no
every
binary
node will have
tree,
two vertices.
but it is given now that 7 nodes are there with 2 child.
so
So we need,
suppose this is the scenario like this. So in that case, how you will calculate
sir, I know that 7 nodes are
like
having
this?
2 children.
No, this is also case. No, so
No,
suppose
this
here
is
1, 2,
another question. Yeah.
8, 9, 10, 11, 12, 13. So here 13, 13 are
Sir,
given.
sir, 5 edges were left, sir. Sir, then how you proceed next?
So 5 is the answer. Here we in the question asking that how many nodes are there with one child.
But there will be no child. How will you get that?
One second. I'm just explaining with the example. So just see this example, okay? So in this example, how many total nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 nodes are there. Okay. So now how many edge are there? So this is n. And how many edge are there? 10. So you can see 10 edge are there. Now just see how many nodes are have with two childs in this. Just look this 1, 2, 3, and 4. Okay, so 4. That means these 4 nodes are actually creating 8 edge below. Okay, so 4 into 2 is equal to 8. Okay, so this is the first one. One second. This is the first, this second, this third, this fourth, this 5, this 6, this 7, this 8. Okay, and after that, so you can subtract by 10 minus 8. Only 2 is remaining. So that means 2 nodes are available with one child. So that actually have only one child, and that is actually creating a one edge below. So you can see that this next one, this node and this one is actually have only one child and creating a one edge below. So that means this 2 is the solution. That 2 is the number of nodes which have only one child are 2. And leaf is actually not creating a edge below because there is no child of these. So these are actually 4.
But can we comment about the number of leaf nodes from these numbers?
Yeah, that can be also figure out.
Yes, we can
So
use
here
the
you can see
handshaking
total.
lemma. Every time it will work.
So total number of nodes are 11. Okay, and two child nodes information are also given. Okay, so 4. So 11 we have total number of nodes. 4 nodes we have calculated, and based on this information we have also calculated this 2 nodes which have only one child. So plus 2 and minus this. Okay, so this is actually you get total. Okay, leaf nodes are 5 actually. Yeah,
Right.
correct, 5.
So it could be another possible question we could expect.
Yeah, that is the possible question.
That's why I'm asking, sir. Just so that we know how to solve it, and not just
Sir, how to
only
determine
one.
this leaf node? Can you just come over again, please?
Leaf nodes, this information is given in the question. So how many total nodes are there? Okay, if you see the question,
Nodes are 20, so we have maximum of 19 edges.
so 20 nodes are given total. Okay, and 7 nodes are given with two child nodes. Okay, so 7 nodes. This is 2. If we calculate n2, okay, this is 7. Okay, so how many n1 are possible? So we can simply calculate 19 minus 7 into 2. Okay, so this is 5. So n1 will be 5. So now how many n0 are there? So simple, just subtract this 20 minus 7 plus 5. Okay, so 7 plus 5, 12 and 8.
Okay, sir.
Okay. Yeah. So that actually log formula, I am not sure that that will work always, because in this type of case, so how you can come, so here you can see height is more, but number of nodes are less.
Yes, sir, it won't work in
So
specific.
it will work for BST, but not for binary tree.
BST also not work.
Not work, sir.
Yeah, we are not saying that our BST is full. BST is also
No, non-leaf
come in the
levels are
form.
full, right? So
No,
non-leaf levels, no.
no. In BST, who said that always that will be always fill? Heap actually heap. If you talk,
Oh, sorry. Yes, sorry about that, sir.
okay. So heap may be full. Okay. So next question in mock.
AVL tree.
Okay, AVL tree. So big 7 is fine. Max heap, that is
10 question. Question number 10.
10th person. Okay.
Question number 10.
Okay, this one. So in the big 7 session, I have explained the rotations, all type of rotations, if you remember. So for creating a AVL tree, you know what are the type of rotations, then you can create.
Sir, in
Then
naval tree question, I just want to ask, like, is it like because if I put it in ascending order and then create the AVL tree,
no
I
order you cannot change.
it produces the same AVL tree, right?
No, it may be
Like the answer.
create another also. So order you cannot change. There is no guarantee that after sorting the elements you will get the same. So here actually some sequence is given. So this sequence is actually said that the inserted order. Okay, we are inserting in the given order node, and after inserting, what they are asking, which of the following nodes would be leaf nodes of T. Okay, so that means leaf nodes we are asking for the AVL. So first we have to create the AVL tree. Okay, so this is also important question. And also you should also know how we create the b binary search tree if the any order is given. Okay, so 36. So first we will insert 36. Okay, so this is single node, so it is not unbalanced. Okay, now we will insert next 20, 40.
To the
Okay,
right.
so 40 will be add on the right. Okay, so we will always compare from the root, and then we will find out the empty place, and then we will add. So 40 will add. Now just check the balance factor. So you know that how we calculate the balance factor. So balance factor is calculated by the absolute difference of left height minus right height.
It is 1.
Okay, so left height is 0, right height
1.
is 1. So 0 minus 1 is, so here you will get 1, but what is the balance factor for 40? 0 minus 0. So there is no subtree on the left, no subtree on the right. So height is 0 on the left, 0 on the right. So 0 minus 0 is 0. So 0. Still, this is balanced. Okay, according to the AVL's condition. If we are getting more than 1, then we can say that this is not balanced. So this is fine. Now we will add next 32. So
Left.
32 will add 36, 40, and 32. Still it is so you can see the balance factor of 40 will remain 0. 32 is also 0 because there is no left no right. And 36, so left height is 1, right height is 1, so 1 minus 1 is 0. Okay, so here also you can see this is balanced. Next is 18. So 18 will add
Left of
36,
32. Left of 32.
40, and 32. And 18 we will compare from the root, so smaller, then we will compare from the 32. So this is smaller, so this 18 will add here. Now just see the leaf node balance factor will be, or slope
Are
you
you
can
writing
say.
something?
Yeah, you right.
One second.
Yeah, no, it is.
Okay, so on
Yes.
balance factor of 32, what will be the balance factor of 32?
1, 1, 1. 1.
Okay, so this balance factor term can be changed. Okay, so in the lecture I think slope term is used, so just don't confuse this. So so 1 minus 0, so 1. Okay, and for 36,
2 minus 1, that is 1.
1, correct. Okay, so here actually we are just calculating the difference of height. Sometimes many of understand that number of nodes, so this number of nodes is not correct. Okay, so height we are calculating left height and right height, not the left number of nodes on the left and number of nodes on the right. So just don't confuse in this part also. So then after then 72 still this is not unbalanced. Okay, now if we add 72 add will here?
Right of 40.
So I'm just looking once again. So this is 0. Now 40 will become 1. Okay. And 36 will
0.
remain 0. Oh, yeah, will become 0. So still this is not unbalanced. Okay. Now 5. When we come on the 5, so 36, 32, and 18, 40, 72. So 5 will add here. Okay. So now this is 0, this is 1, this is 2, and this is 0, this is 1, and here 3 minus 2, this is 1. Correct?
Yes.
Okay. Now you can see we are getting one valence factor greater than 1 on this 32. So this, what is the type of this unbalanced? Okay. So here just see which part where the balance is increased from 32. Left side or right side?
Right side.
Left, left side. Okay. Now just move on the child of 32. Now from child, just see that which side the balance is high. Height is high.
Left
Sorry,
side.
high is high. Okay, so
LL.
left. Okay, so
Left
this is
side.
LL condition, left condition. So in this case, we apply the rotation on the node which have two balance factor, and we just rotate clockwise. Okay, by selecting this as a pivot, and we just rotate as a clockwise. So after rotation, you will get this type of tree, 40 and 72. And
So what is this LL, sir?
sorry.
What is this LL you have written?
Uh, okay, so that things actually you have to go through the week 7 session. Actually, there are four type of rotations where we have discussed in the session, and according to these rotations, this four type of condition we apply some rotations. So that actually the long part. If we discuss today, so I think 1 hour is required to discuss this.
Okay, sir.
Okay, so can you go through the week 7 open session?
Okay, sir.
Okay, once to understand these rotations, and also these rotations are given on the here slides in the notes
Okay.
in the week 7. If you see this week 7 part, so there is one slide is given, AVL tree. So you can also see this in this slide. So left rotation,
Okay.
okay, like this. Right rotation, right, left, left, right. All the situation are given.
Okay, sir.
So this is in GitHub, right?
GitHub notes.
Okay.
Okay, so in this case, we will rotate this, and 32 will add here, and 5 will come here. Now this is balance. So 0, 0, 0, and 0, 1, 0. Okay, now how many nodes are remaining? So this 35 and 34. So 35 we will add in this. So where this 35 will add? So
Right.
36, 18, 40. So 35 is smaller than 36. Okay, so let's come on the left. 5, 32. So 35 is smaller than 36. Move to the right, left. Greater than 18. Move to the right, and greater than 32. So 35 will add here. Okay, so after inserting this 0, 0, 0, and this 1. Now balance factor of 32 will become 1, and 18 to 1 minus 2, 1. And what is the left height of 36?
2,
4, 4.
2,
Longest path is 4.
3 minus 2.
3, 3. Sorry.
3. Okay, if you are counting the edge, so then 3. So right side is 2. So 3 minus 2 is 1. Still, this is balanced. Okay, so no need to rotation. So now next one is 34. So 34 will add here. If you check, 34 is smaller than 36, greater than 18, greater than 32, smaller than 35. So 34 will add here. Okay, so now if you calculate the balance factor again, so you will get 0 here, 1 here, and 2 here. Okay, and 0. And also for 18, so right height is 3 and left height is 1. So here also 2. Okay, and 0 1. And for 36 also, okay, so 1 2 3 4, and right side is 2, so 4 minus 2 is 2 is also here. Okay, so in this situation we always select the 2 which is coming from the first, from the bottom side. Okay, so from this bottom side which is coming first. So here this 32 is coming first, which have 2 height balance factor. So we will just apply the rotation on this. Automatically the above balance factor will reduce after making this as a balance part.
Sir, this
Okay.
is right left condition, no?
Ha ha ha.
In right left condition, how we
Yes.
move?
Okay. So from 32, which side we have height? Right side. Okay. And from the child, which side we have more height? On the left. So this is RL type of condition. In RL case, first rotation we apply on the child. Okay. And this rotation is actually clockwise. So first we will apply this rotation. So, okay. So 36, 40, and 72. Okay. 18, 5, 32, and after rotation this. Okay, so this 34 will come here and 35 will shift right. Okay, so this is after first rotation. Then second rotation we will apply on this, and this will be the anti-clockwise. Okay, and after this rotation, so this is second rotation. So 36 and 40, 72 and 18 and 5, and this 34 will come at 32 position. So 34 and 32 will come on left, and 30 this 5, 35 will come here. Now you can see balance factor 0 0 and 0 0 0, and for 18 1 minus 2 1, and 40 is 1. Now 36 3 minus 2, this is also 1. So you can see above node which have which had balance factor 2 in the previous, that is also reduced. So this is the final AVL tree we are getting. So 5, 32, 35, 72. So these are coming as a leaf node. So 32, 35, 72. So these option you need to select. So 5, 32, and I think 32, 35, 72. 32, 35, 72. Yeah, so these option you need to select. Okay, so to solve this problem, just first understand the rotations part, and then just practice with the small sequence. You can randomly take any sequence, okay, for 6 7 element in unordered situation, and just try to create a AVL tree.
Sir, the
Then you
root
will
balancing factor was 1, right?
hmm, uh, for this final one.
Yes. Yeah, for
Yes,
the
yes,
final one.
one. So you can see left height is 3, right height is 2.
Okay, sir.
Okay, so 3 minus 2 is 1. Okay. So
Sir, what are the all three, four cases in rotation? Could you write that?
okay. So I'm just writing that. Okay. So first case is when we are getting this type of situation. So like, okay. So here we are getting 0 valence factor 1 and this 2. Like, okay. So this is actually L case. In this case, we always apply the rotation on this 2 valence factor node, and that is actually a clockwise rotation. So this, suppose I'm writing this A, B, C in this way. So this will be rotate like this. So B will come at the top and A will shift here, and this C will come here. Okay, so this is LL rotation, LL situation. Just opposite the case is RR. Okay, so RR case is like A, B, C. Okay, so our node is connected in that way. So this balance factor is 0 here, 1 is here, 2 is here. Okay, so now this time we will check from the root this 2 balance factor node. So right side is height is more, And from child node, right height is more. So once again R. So this is RR case. Okay. In this case, we apply the rotation anti-clockwise on this node. So this become similar B, A, and C. Okay. So these are two LL and RR type case. Next type case is LR. So LR situation. So suppose A and one node is connected like B here, and this is connected like here. Okay. Now the balance factor of this is 0, this is 1, this is 2. So in this case, you can see from A, so height is increased on the left side, but from B, height is increased on the right side. So this is LR case. In this case, in this type of case, we apply two rotations. So first on B, okay, and this rotation is actually anti-clockwise. So after applying this rotation, so this is first rotation. So we will get this type of tree A and C and B. Okay, and on this rotation, second rotation we apply on the A, and this is clockwise rotation. So C will come at the top and A, and then B. Okay,
So in short, we can say that the middle element will always come at the top, and the
no, we cannot say anything this type.
because C, sir, C is the middle element, so C has come at the top.
So this is depend on the our case. So how C is coming in the middle after first rotation.
After second rotation, C is in the top, sir. C is in the top.
So that is actually we will select what pivot element we are choosing. So this C will come at that place. Here we are selecting A as a pivot, and we will shift the C as the A place, and A will move to the right side.
Okay.
Right child. Okay, and the opposite condition is RL. So RL situation is like RL A and B and C, like this. Okay, so height is more on the right from A. Okay, so 0, 1, and 2. Height is more on the A on the right side. So we will move to the child, and height is more on the left side from B. Okay, so this is L. So RL type of situation, first rotation we will apply on the B, and this is the clockwise rotations. After applying this rotation, we are getting like A, C, and B. And second rotation we will apply on the A, and this is anti-clockwise rotation. So C will come here, and A, this is B.
The value wise, C is the middle element. Na? A is the largest element, and B is the smallest element, and C is the middle element. A is the
So this is actually binary search tree. So definitely this condition will be satisfied. So the left child should be smaller and right side should be greater.
so the middle element is always coming in the top, and the lowest element is always coming left side, and the highest element is always coming on the right side in both the conditions.
Yeah, in subtree you can say that in subtree part which we are actually rotating. So this subtree, so maybe the above the remaining tree is also connected on this part. So if you see the previous example, so we apply some rotations on the lower part. So suppose in this part, okay, so we are simply selecting this part for the rotations.
Yes.
Okay, so yeah, in subtree after rotation you will get the BST condition satisfied.
So 34 is coming at the top, 32 is coming in the left, and 35 is coming in the right.
Yeah. So actually, this rotations is actually give the insert this thing. So after rotations, your tree will remain binary search tree.
Yes.
So binary search tree condition will remain satisfied after rotations. Okay. So for the details rotations with the example, just see week 7 open session.
Okay, sir.
Okay, here where we just apply this rotation with
No,
the
sir. Now
examples.
it is clear, sir. These four are the main. Now we need to do. Now there is one more case. No, before checking
Yeah.
left, right, we need to balance the bottom. Means if right is not balanced, so
No,
we
there
will
is
do
one
like
more.
that.
There is one more case when if we are rotating, and okay, one second. I'm just mentioning with that case. So like 10 and 20 and like 5, 6, and 2 and like 1. Okay, so if you see in this case, so this is 0, this is 1, this is 1, this is 0, this is 2, and this is 0. Okay, so before this, when we, if you see this part, okay, so there is that tree is balanced actually. So but when we are adding 1, so it become a unbalanced because we are getting 2 at this 10. Okay, so what is the this type of case? Okay, so in this case you can see the from the two this 10 nodes. Okay, the left side is a height more. Okay, so this is L case. From the left child, just see from the 5 node, and which side height is more, left side. So this is also a LL case. Okay, LL case. So in this case we apply the clockwise rotation on 10. So when we are applying the clockwise rotation on 10, this 5 will come on this place. Okay, so we will shift this 5 as the here. Now this 10 will move to the right. Okay, and 20 will shift it more, and this 2 will
Left
remain
from
connected
left
on the.
to 36.
Now this 6 is actually which is connected on the right before on the 5. So where we need to connect this?
Left of
Left
So
side, left
this
of
will,
top.
yeah, this will connect here. Okay, now you can see our BST property is satisfied.
This condition is there in the lecture. This
Ah,
condition is there in the lecture.
yes, that is also mentioned in the lecture.
Sir, mock question 2. Why would Dijkstra work? Although it kind of works, but
Mhm.
like, is this like this seems like a general case question to Dijkstra.
Okay.
Bellman-Ford obviously will work, but
In that particular case, it worked. It is
yeah,
not
in
true
that
for
particular case it works. Yeah, otherwise it
that
doesn't
question
work.
is for that only. Yeah.
Yeah.
Question number 2. Okay, this one.
It's like because from the starting thing we have all the negative edges and everything else is positive.
Huh. Okay,
No
so
negative.
if you see the source is S, and from S there are 3 edges which is going outside. Only that contains the negative weights.
Hmm.
Okay, and other edge are actually contain the positive weights. So it will not create a problem. So why it will not create? So first thing you have to understand that in which case actually the Dijkstra algorithm return the incorrect output for the negative weights.
Hmm.
Okay, so I'm just taking 3 nodes. So S, A, and B. Okay, so like this, S is connect, B connect, and this is C. So if we are mentioning this 5, and this is 2, and this is -4. Okay, so here we have taken one negative weights, but this is not creating a cycle. Okay, this is not a negative weight cycle. Okay, first we will start Dijkstra from S, and after selecting S, we will check what are the distance we are getting for A and B. If we are create a table like this, A, B, so first S, this is source node. Okay, so 0. For A we are getting 5. Okay, and initially that was infinite, but after considering this neighbor edge, we are getting 5 distance from source, and for B we are getting 2. Correct. Now what we will do, which node we will select next according to the Dijkstra algorithm?
B.
B. B.
B. Okay, so B we will select first. So we will select B, and from B we will look which node we can update. We cannot update anything from B. Okay, so now we have marked that S is visited and B is also visited. According to the Dijkstra algorithm, we never look the nodes which have already visited.
Yes, we
But
got.
here actually, when we are going to A, when we are going to A, after the selection of B, there is no update, but the next node we will select A. Then you can see we are getting -4, and the weights are at A is 5. So 5 -4, we are getting 1, which is smaller than the previous 2. Okay, so but it will not update because we have already visited B. So we will not update this.
The dash
So
star
you,
will not work.
so in this case, dash star will fail. So at any time, if our edge, the negative weights edge is coming from the non-visited node to visited node, that will create a problem. Okay, but if our non-negative edge is coming from non-visited node to non-visited nodes, sorry, visited node to non-visited nodes, that will not create a problem.
Okay.
Okay, I just changed this reverse condition, so like I'm
So,
making this as a 2 and this is 4. Okay, so in this case first is s a b, so s is now 0 and a is infinite. So when we are visiting s, so we will update the a and b, so a will become 2 and b will become 4. Okay, so then you will select a first. Okay, so a first, so after selecting a, so this will be considered. Okay, because b is not visited right now, so here this is a is visited but b is not visited, so this condition is okay. In this case we will not the our sort of weight is not affected. Okay, so we will get 2 minus 4 is minus 2 for b, so b will update minus 2. Now next we will select b, so this is, there is no update, so we are getting correct solution. So any case if so this edge, so a b and this is contain actually minus negative weights, so if this a is non-visited and b is visited, so that will create a problem, but in the otherwise that will not create a problem. So for the given graph actually our 3 edges going outside which contains the negative weights all are the case, this s is visited but all 3 are not visited. Okay, so that will
so,
not create a problem.
so like from A to B, so like if B is already visited, then we have a problem. Otherwise,
Yes.
we don't.
Hmm. Okay, so because we in dash algorithm we never update the nodes which is already visited, and if our any edge is going to the visited node and which contains the negative weights, so that may reduce the weights of the visited node, but we cannot update that node, so that will create a problem. Okay, so this is the things actually when digital algorithm not works. So in the graph actually this is the scenario where the digital algorithm will work. Okay,
Yes, sir.
any other question in mock?
Sir, Prims is also similar to Dijkstra, sir. But in Prims, there is no case of negative. Is this
Actually
because
we are calculating the total weights, and
in Dijkstra we are calculating total weight, but in Prims we are just getting the age, right?
no, not
We are
in the
just getting the tree, not the.
uh, actually in the Prim's algorithm we are calculating the minimum total weights on the edge, no shortest path like this.
Yeah, actually in Dijkstra we are getting the sum, right? We are going from
Some of the
somewhere.
all edge, yeah.
Sir,
Yeah,
question
right.
8.
Question 3.
8.
Question 3.
Question 3 of this. Okay, so for this node, this question you should know the Dijkstra algorithm working. Then you can directly apply the Dijkstra algorithm dry run. But, okay, so in this case we will start
The
from the
minimum
A.
distance from A to H is 6, but the option is saying it is not correct.
No, A to H is 5.
How you are getting 6?
Sir, A to D, D to E, E to H.
This is 5. A to H is 5. Yeah.
How, sir? Please, can you?
So you can see in the diagram graph A to D and D to E and E to H. How you are how much you are getting? 5. I think you
okay.
just look this A to D
Yeah,
and D to
I
E.
also made the same mistake, sir. Sir, question
Okay.
8, that priority queue can we do, sir, or you already did, sir? I was late to the session.
Which question?
Question 8, priority queue.
No, that I not actually discussed. Okay, so don't try to solve this question on directly by looking the graph. So maybe that you can do some mistakes. Just apply the dry run of the digestion algorithms, and then verify the answer. Okay. So is there any need to solve this, or you can do?
No,
Not
this
required, sir.
Okay, question 6.
Sir, question 8.
8. Okay, so a priority key is implemented in max heap. So this is max heap. Initially, the max heap is this. Two new element 10 and 70 are inserted in the given max heap order. Max heap after insertion of the element is okay. So this is simple insertion of in the max heap. So you have given one max heap. Okay, so you can create a max heap 20, 18, and 15, 30, 13, and 12. So this is the max heap given.
Sir, you're
Okay,
not visible, sir.
not visible. One
No,
second.
you're writing something, it's not visible.
I'm writing. What happened?
Sir, I think you should share again.
Now,
Now it's
yeah,
Okay.
this much, this is up to this, okay, sir.
Mhm. Okay, so yeah, this is the first thing. Max heap is given. Now two new elements. Okay, so just add 10 first. So where 10 will insert here,
Yes, sir.
correct? And
Yes,
this
sir.
is a max heap. Uh, so I think it is not violating any max heap property. So if you
Yes,
look this, so
yes,
this is okay. So always check these things with the parent node. So 10 and 15. So this is in the correct order. So there is no problem. So after insertion of this, just add one more 17. Okay, when you are adding 17, so just compare the 17 and 15. So the order is incorrect. Just move the 17 at the 15 place. Okay, so 20 and 18, and this 17 will come here, and 15 will move to the 17 place. So 15 will come here. Okay, 10, and this will remain same, 13 and 12. Okay, and anything else is to given, and the driven maximum after, yeah, so this is okay. So 20, 18, 17, 13, 12, 10, 15.
correct, sir. I don't know why I made a mistake, sir.
So this is the simple one. I think
The simple
nothing.
one only. I
Yeah.
made a mistake. I don't know how I made it.
Otherwise,
Right.
the complex question is also be asked in the
So
previous
maybe
one.
while selecting, I selected wrongly or something like that.
Mhm.
Yeah. Yes, sir. This is
So
Sir,
in the
question 9.
question
okay,
9.
so related to this max heap questions, actually, sometime many times the this type of question is asked. So some sequence is given, one heap is given actually. So some element is asked for the insertion, then delete max like this. Okay, so suppose we are asking here to insert 17 first, then perform the delete max operation like this type of operation. Okay, so practice on this insert and remove operation on the heap for every type, min or max. Okay, ninth question. So this is three array max heap. So here you have to maintain three child for each node. A3 array max heap. Okay, so like when you have two children and this is information, the root is stored at location A0, fine, A23, so this is definition. Suppose elements 6, 1, 12, 8, and 9 are inserted in that order into a 3 array max heap. This. Okay, so max heap is given. Okay, so 10, 4 will come at the first child, 5 will come as a second child, and okay, correct. 7 will come as a third child. Then 2 will come here, and 3. This is the order, and we will insert 6 first. So 6 first we will insert 6 at here. Okay, and then see the comparison of with the parent. So 6 and 4. So 6 should become at the 4th place. So after insertion of 6, you will get like this. So 6, and this will become 2. This is now 3, and this will become 4. Okay, and remaining will same. Okay, next will be 1. So 1 will add at the 5 first child. So I think it is not creating any problem. So now 12. So 12 will insert at the second child of 5. Okay, so 12 will shift at the 5 place. Okay, so that means 10 and 6. This part will remain same. 2, 3, and 4. And here 12 will come, and 1 and 5. Okay, and remain 7. Okay, now 8. So 8 will add at the third child of 12 now. Okay, now you can see it is not creating any problem because this is still maxi. Now
Sir,
9.
12, sir, 12 will go up. No, sir, 12 is bigger than
Oh,
10.
okay, I missed it. Sorry. Yeah. So and then 12 and 10. Yeah. So this 12 will move to the top. 12, okay, 6, and 2, 3, 4. And then this 10 will come here, and 1, 5, and 7. Yeah. This is the update after adding 12. Now when we add 8, so 8 will add here, but it is not changing the this maxi property. Yeah. Next is 9. So 9 will add below 7 as a first child. So 9. So now we will swap this. So 12, 6, 2, 3, 4. Okay, so 10, this 1, 5, 8, and this will become 9 and 7. Okay, so this is the final version, and just give the order of this. So 12, 6, 10, 9, 2, 3, 4, 1, 5, 8, and 7. This is the answer. Okay. So I think first of what we are getting 7, 587. So 587 is third answer. Yeah. The next question.
11.
Okay, so this is based on the properties of Hofmann. Oh, sorry. Excuse me. Okay. So some properties are given. So which property it is not clear here? Because the second and third, I think it is fine. So Hofmann code algorithm always generate prefix code. So this actually is the property of Hofmann codes. So if you see that if we are getting, suppose we are creating a Hofmann codes for A, B, C, and we are getting 0, 1 for A like this. So we cannot get the code like 0, 1, 1 for B. Okay, here you can see 0, 1 is coming at the initial as a prefix of on B. So this type of situation cannot be come in the Hofmann codes. Okay, so this is the property of Hofmann codes. So this type of condition will not come in the Hofmann codes. So then our codes is called as a prefix codes. So this is true, and Hofmann code algorithm is based on greedy approach. Yeah, this is also true. We are following the greedy approach. We are always selecting the two smallest weight, and we are creating a Hofmann tree. Okay, and we are repeatedly performing the same things. So this is also true. And the first property, yeah, this one. So here in an optimal Huffman tree, if leaf labeled X is at depth smaller than, okay, so in finally we are creating, we just get this type of Huffman tree. Okay, so this is complete, sorry, strict binary tree like this. Like this, okay. So here it is mentioned that if X is at depth smaller than Y, okay, so that means if X is coming at this level, the from the depth from the root, so, and Y depth is more than this X, so suppose Y is coming at lower, okay, or leaf node, if we are talking about the leaf nodes actually, so this is the character leaf labeled, okay, so this is like a X and this is like a Y, okay. So here this condition is given, then frequency of X is smaller than frequency of Y. So frequency means the value which are given for this X and Y.
This is not true.
So this is not true because we always select the smallest value first. So here this X is smaller than Y. Then Y cannot select before the X. Okay, so we always create the Huffman tree from bottom to up side. Okay, so that means these two values are selected first. That should be smaller than the remaining one. Okay.
So the way to think about it is Huffman algorithm is about compressing data, right? So anything, right? So anything that is high frequency will be in the upper level because they'll get less bits, so they will achieve most compression, right? So we can see that anything with high frequency will be in the top of the tree. Anything in the low frequency will actually be towards the bottom, which will get more bits, right? So since X is happening on the shorter length, shorter depth, then you can pretty much conclude that X is appearing more than Y. That is why it is closer to the top of the tree.
X is at bottom, so X frequency must be less, no? X is at bottom at depth.
No, Y is the bottom.
So but it is saying X is depth is smaller, sir.
So depth smaller means depth smaller value. Okay, so 1 second. The leaf label X is at depth smaller than leaf label Y. So this depth value, so this what is the depth of this X is smaller than the Y depth. So if you count this depth by the path length, so suppose from root, so number of edge, so you are reaching this X in 2 edge. Okay, so this length.
Okay, sir,
you are getting
got it,
3.
Sir.
Okay, so this 2 is smaller than this 3.
Okay, I misinterpreted the statement, sir.
Okay.
Sir, if this question would have been less than or equal to, then in some cases it will suffice, but not all cases. Is that correct?
Yes, equal may be possible.
Equal, not all cases, or I think only some cases.
No, sir.
Will that be all cases sufficing?
Sir, when depth is smaller, obviously the frequency will be more only, no, sir?
Yes.
No, that is not the case. Actually, that is not the case. So sometimes actually this is also the one case. So we are getting this situation like this is leaf and this is leaf and this is leaf and this is leaf. Okay, so we have 4 frequency like 2, 3, and 4 and
at the same level, right?
1 second.
All the frequencies are equal.
So like 2, 2, and then 3 and 3 like this. This type frequency is also possible.
But depth is same.
In that case, depth is same.
But here they say the depth is smaller, no, sir?
This is given depth is smaller one. So definitely this condition is given.
So frequency is increasing. Sir, when we are having only 4, sir, 4 things are there, and all are frequency same. Why shouldn't we use only 2 bits for the any 2 and 3 bits for any other 2? Why we have to use all equal, sir? Any condition is there?
No, how
For
you will
example,
decide the bits then?
at
Here,
0, 1 we'll
this is
get.
not only the bits. We are also creating a codes that should not be that should be the prefix codes actually.
Sir, in the tree which you have drawn in the left side, it is
Uh,
not necessary that the frequency of 1, 2, 3, 4 are the same, right, sir? Because one will be the lowest, one will be the lowest frequency, two will be higher than one, three will be higher than two, and four will be higher than three, right, sir?
no, which graph you are talking about?
The
Left one or right?
leftmost graph which
This
you have,
one.
yes.
Okay.
It is possible that all are equal, but it could also be possible that
So suppose if this is one, this is two, this is three, and this is four.
right.
Okay. So in that case, when we are adding one and two, so we are getting three here. Then we have to add this three at this place
Yes, yes.
in the next level.
But suppose the combined frequency of 1 and 2 is less than 3. Combined frequency of 1 and 2 is less than 3.
Hmm. Then
Uh,
you will select like this is the case now. So suppose you are getting one and you are getting one. Then next node is three. Okay. So you are getting two. You will get add here three like this.
okay. Right, right, right.
I think when it is Fibonacci sequence, right?
So in this, is it always true that 1, 2, 3, 4 will all have the same frequency?
No.
1, 2, 3, 4 may not have the same frequency, right, sir?
Frequency means
Means the
frequency is only storing on the leaf node, the actual frequency. This
yes,
we
yes,
are getting internal node. We are getting the sum.
yes, yes. But
Okay.
the frequency of 1, 2, 3, 4 is not necessarily the same, in the graph which you have drawn in the upper left corner.
So frequency can be anything.
Yes, it is not necessary that it is equal, no, for all
No,
of
no,
us.
no, no, no.
Okay.
Frequency may be anything.
So actually, it is told if there are some symbols and the frequency follows a Fibonacci sequence, then it's a special case.
Why special case?
So because when we are grouping, let's say in this example, the two nodes we add, the next one on the list, their sum is also similar to this. There's a tie, so they are on the same level, and then kind of
So here no tie. Actually, we will always select the two smaller one now.
yeah.
So we can
So
select any two. So it will not affect anything. So suppose you are getting the Fibonacci series. So like one, two, three, and then five like this, eight.
so what I'm saying is, let's say 1, 2 is the first two, then the
Ha,
next frequency is actually 3,
ha.
sum of the previous two numbers, right? And then the next one in the sequence is also equal to 1 plus 2 plus 3, which is 6. So essentially, like if my frequency follows like the sum of cumulative sum of all the frequencies, right? Like very much typical to what a Fibonacci sequence looks like, because what the sequence says is the next term is basically equal to the sum of frequency of the previous two terms. If you look that will be a Huffman code with the highest length. It's a special case.
Okay, so here if you are adding three here, yeah, so height will become high in this
Yeah.
case.
So again, a quiz
Five,
question.
then five.
What will be the instance where you get a Huffman code tree with the highest length?
Okay, okay. So that we will ask in the next quiz.
Sorry, sir.
Yeah, that type of question can be created.
Sir, what?
Sir, he will be TA. He will tell all the things.
Yeah. So we can give some sequence and then we can ask which type of the sequence can be created
Sir,
highest.
I think in this upper left corner graph, the frequency of all 1, 1, 2, 3, 4 will be the same, sir. I think so. Because they all have
No,
this.
this is depend on the example. So suppose one we are taking and then three we are taking. Okay, so this will be selected as a first node, and no, no, no. Okay, one second. So one and 1. Okay, we are getting 2. And next is also 1 like this.
So next is 2, sir, like Fibonacci, like 1 plus 1, 2. Next frequency,
No,
whatever the
that is
symbol.
not the case. Actually, he's asking that can we get the all frequency length same?
Yes,
Okay.
sir. They have to be same because
It may be, yeah, the possible, yeah.
Because if they are different, suppose this third node has to be higher than 1 and 1. That is, suppose it is 2, then 2 will be paired with the sum of first two nodes, right? And 2 will be paired with the sum of the first two nodes. It will not appear as a third node. So it has to be 1 only. It cannot be 2.
Yeah, this type of situation is also possible. So suppose here you are getting 1 plus 1 and you are getting 2. Okay, so next we are getting 2, 2, 2. Okay, so we can select any 2. So we can select also these 2. Then we will get 4.
Can select any 2.
We can select any 2.
Okay.
Okay, so in this case we will get 6 like this. So you will get the all same length.
So that's another quiz question. How many possible Hoffman trees are possible when we have ties?
Yeah, correct. Okay. So next, any question in this?
Sir, if we are able to solve the mock, we should be like good for the quiz, right?
Yeah, actually, this mock we picked from the previous quizzes questions. Actually, the all questions are taken from the previous quiz.
No, sir. What he meant was whether the similar type
No,
of
no.
questions
If you
or
are thinking that after only solving the 16 question, and you can do well in the quiz, so that is not guaranteed actually.
Oh boy. No wonder the average is 50%.
Yeah, but you should complete all these 16 questions and you should understand the concept behind to solve these questions.
Yeah, like, if you understand the concept, that is what I was asking.
Apart from that, you should also know the all remaining graded questions, practice questions, all the concept algorithm
That
concept
we
also.
have done.
sir, but
So,
most of the things actually from week 1 to 4, not much of question will come, sir, in quiz 2.
No, that part will not involve. Maybe some so that actually complexity part. Okay, so
BFSS
complexity start in the week 2, then it will remain till week 10 or 11. That will always use. So that is interdependent actually. Okay,
Other
so
than
some
that,
top we
yeah.
are using some concept from the previous week in the next week.
Sir, question 16 also.
Hmm. So because of that, we just said that the syllabus will be from 1 to 8, but mainly from 5 to 8. Okay. So before 16, any question?
Sir, this 15 question, we just have to apply the algorithm and we're getting the answer, right?
Yes.
Nothing
So
else.
algorithm code is also given.
Yes.
No need to follow. If you know the mom's algorithm, median algorithm, directly just create a
This
7 7 partition and just pick the middle element. Then once again apply the same.
it's a very sweet algorithm.
Uh, okay. So before this,
Give such type of questions, sir.
okay. So, huh,
Say +1.
Oh, this being recorded.
paper is already set. Okay, so this 16th questions. Hmm. One second.
Sir, please teach the master method, sir.
I also don't like master method. Too long way. When tree method can solve easily this, so why we use master method? So tree method is difficult for you? there are only three condition is given in the tree method. If you know these three condition, you can easily determine the complexity.
Sir, which method? Tree method? Sir, substitution method I only know, sir.
No, recurrence tree
No,
week 8.
recursive.
In week 8, there is one topic, recursion tree, and that is the way to calculate this complexity. Yeah, this one, recursion tree. Okay, so we can simply convert the form of this recurrence relation, and based on these three conditions, so this last three conditions, decreasing, equal, and increasing, you need to remain keep these conditions in your mind, and based on these three conditions you can identify the complexity. Now check some example for this. So suppose the first case, okay, one second. So first case, so t n, I'm writing that way, equal to 9 t n by 2 n by 3, sorry.
It's not visible.
Okay, one second. Okay.
Now it is.
So we will start like this tn, okay, and we'll create a logical tree diagram. So we are starting from tn. Now you can see that how many childs we are dividing here. 9 child.
Nine childs.
Okay, so 1 2 3 4 5 6 7 8 9, like. Okay, every sub problem size is n by 3. Okay, and in this process the remaining time is also required order of n. Okay, so t n by 3, t n by 3, like this till last, t n by 3. Okay, so here order of n is required, so total we can write n. So when we are passing n by 3 size, so when we are passing n, we are getting n operation apart from recursive call. When we will pass n by 3, we will get n by 3 operations here. Okay, so for this sub columns we will get n by 3. Same for this child, n by 3. Okay, same for this, n by 3, like this. Okay, so if we add all, so 9 into n by 3.
3n.
Okay, and we are getting 3n in next iteration.
Increasing sequence.
Okay, once again, each child have 9 sub problems. Okay, and that will become n by 9. So n by 3 multiply by 3, so n by 9. Okay, n by 9, like this. 9 for one child, so total are 9 child, so you will get 9 into 9, 81. So 81 child, and each have size n by 9. Okay, and this is 9, and we can write 3 square n. Okay, and this is 3 1, and this is 3 0, we can write. This part is clear?
Yeah, yes, sir.
Yes, sir.
So you can see the pattern now. You are getting n, then you are in the next level. How many operation is now? 3n. Next level, you are getting 9n, and we can write 3 to the power 0 n, and 3 to the power 1 n, and next level 3 to the power 2 n. So you can see that every level number of operation are increasing. Okay, clearly seen. Now just see this condition. Which case? We are getting the third case. Okay, so increasing case. You can directly pick this expression tn equal to big O n log n to the power log cr. Okay, and that means tn equal to n log cr. And what is c and what is r here? So c is
3.
3.
R is 9.
So in this recurrence relation, so this is actually called as a recursive call r, and this is called as a size which we are dividing. So this is called as a c. Okay, just put this value in this expression. So n log, the C is now 3 and R is 9. So we can write it in that way. So 3 to the power 2. This 2 will come at this first place, and 2 into log 3, 3. So this will become 1, and you will get n.
Sir, this
square.
R and C, what did you say? T and...
One second. Huh. So this R, when we write this recurrence relation, na, so in recurrence relation, this is okay. I'm writing again in the clear. So T N, okay. The form is actually R T N by C plus Fn. This is the form of recurrence relation. Okay, R is representing the number of how many times we are calling recursively in the next iteration. So this is representing R. C is representing the size, what size we are passing in the next recursive call. So this division part, and Fn is representing the time, what time is required apart from this recursive calls. So this is Fn. Okay. So now after that, by this recurrence relation, just create a tree and see this pattern, label wise operation patterns. Just see, it is increasing, it is remain constant, it is decreasing. Only 3 cases are possible. If it is increasing, it is constant at each level, and it is decreasing. So based on this 3 condition, you can just apply this formula. So in this case, we found that our number of operation at each level are increasing. So we will apply this formula, and we will put simply this value C at R value, and we are getting n square complexity. This. Okay.
So Fn is time, R is the recursive call. So N by C is the recursive call, right?
This is input. How we are dividing the input in the next call. Okay, just look the simple merge sort recurrence relation. Okay, so Tn equal to 2 T n by 2 plus n. Okay, this is the recurrence relation for merge sort or best case quick sort, like this. So if you draw the tree Tn, you are getting 2 child, Tn by 2 and Tn by 2. Okay, next is Tn by 4, Tn by 4, Tn by 4, and Tn by 4. Okay, now if we are passing n input, n size, you are getting n operation. Okay, and if you are passing n by 2, you will get n by 2 operation at this place. Okay, same, you are getting n by 2 plus operation. If you add both at this level, n by 2 plus n by plus 2, so here is n. In the next level, n by 2 plus n by 2, n. Okay, here n by 4, n by 4, n by 4, n by 4. That means 4 into n by 4. Same n. Okay, next level you will get 8 into n by 8, n. Okay, that means you can see every time at every level, number of operation are remains same, not increasing, not decreasing.
So O of n only.
So this is the case when the second case, which is equal case. Okay, all terms in the series are equal. So you can directly pick this formula, big O Fn log n. So Fn and log n. So what is the value of Fn? You can directly pick from the recurrence relation. So what Fn value is? This n. Okay, so we will write complexity like this, T Fn log n. So what is the value of Fn? N. And directly put n log n. Okay, so this is the case when our operations are remain same. We have already seen increasing case and this constant case.
So in the quiz one, actually we got the question like this. Instead of n by 2, it was actually n by 3 and 2t by 3. That is what we got.
That is possible. So just see the pattern, the number of operations increasing, decreasing, or equal. Okay, so the remaining example is for decreasing case. Okay, so if you remember the big 8, this algorithm, if you remember,
2t 2t n by 4, sir.
that is also possible. Otherwise, I'm just looking this quick select recurrence relation. Okay, so I'm just writing the quick select recurrence relation. So Tn in the next iteration, so in quick select, every time we discard half part. Okay, that is actually the purpose of quick select, is to finding out the kth largest or kth smallest. So we perform the partition process. Okay, we perform the partition process, but after selecting the pivot, we select only the one half part, either left or right. So that means in the next part we call the same algorithm on the half part. We skip the remaining half part. So that means next part is like t n by 2. Okay, and to perform, apart from this recursive call, we are performing partition process. So that is taking actually n time. Okay, so this is the recurrence relation for this quick select algorithm. So how we achieve this complexity order of n? So just draw this case. So this is like tn, and next is only one call. Okay, so here tn by 2, and next is tn by 4. Okay, so here you are getting n operation. If your input size is n by 2, the n by 2 operation. Then next is n by 4 operation. So here actually the operation are decreasing. So in decreasing case, you can just pick this direct formula, decreasing tn equal to fn directly. Okay, so tn, what is fn given? Fn is given n. So directly below of n. This is the complexity. And you also mentioned this one recurrence formula like this. So tn equal to what you mentioned, 4 2 tn by 4.
2t n by 4 plus n.
And yeah, this is also one example for decreasing case. So tn, if we draw this tree for this, so there are two child. Okay, so t, and size is n by 4, and same t n by 4. Okay, and here next level is t n by 16.
How, sir? 8
t
4.
4 into 4.
Okay. You're
Okay, n
dividing
by
n by 4, 4
4
by.
by 4. So it will
Okay.
become n by 16. Okay, n by 16, and this t n by 16, n by 16. Okay, if you see the number of operations each level, first we are getting n. Okay, next level n by 4 plus n by 4, 2
n by
into n
2.
by 4, you are getting n by 2. Okay, next level you are getting 4 into n by 16, then n by 4. Okay, you can see this time it is decreasing, and n by 2, n by 4. So same things, you can write the complexity tn equal to fn. So what is fn? N. We go n. Correct.
Sir, one question, sir,
The
after
three
this.
formulas we have to remember, no, sir?
Yes, yes. So just remember this
Decreasing
three formula.
decreasing f of n, increasing that f of n power log c
Log
r
CR,
equal means n log n. I mean fn log n.
fn log n. Yes. So some formula is not too much difficult. You can remember this.
Sir, one
And,
question.
sir, one more before
Ha,
that. F
ha,
of
ha.
n can be like plus n or plus 2n if they are given, then we have to take 2n, sir.
No, fn is given like 2n. So just read the n.
And
Remove the constant part.
yeah, asymptotic. Okay.
Yes, Biswas.
Sir, where you solved the question, please.
Sorry.
So can you open that page where you solved the question?
Okay, okay, okay,
Just
okay.
the question.
Which
Sir,
one?
the above one. The above one. Sir, you said in this the relation is t of n by 2 plus n. So in binary search case, it is t of n by 2 plus 1. In
Yes.
that case, it should be order of 1, but it should be order of log n or y order of. In that case, it will fail, sir. The recursive relation is
So
t of n by 2 plus 1. If we take
because
fn in that case,
what happening if this is one, okay, I'm writing the binary search. Tn equal to Tn by 2 and plus 1, correct? So
yes,
if
sir.
you draw this, so Tn, next is Tn by 2, okay, next is Tn by 4. But what operation is required when Tn is 1? Next, that means this 1 is totally independent on the size. Still remain 1. Still remain 1. Correct? So this is the equal case.
Uh, okay, sir.
Okay.
Okay.
In the equal case, we are
Okay.
selecting Tn equal to Fn log n. Okay, Fn is now
Okay.
1.
Okay.
So 1 log n. And we are getting log n.
Sir, I thought we will solve that t of n by 2, so that will give log n, but we
No,
will
no.
select that ff.
We just write this number of operation based on this Fn part.
Okay, sir. Now understood.
Okay. Yeah. Okay, so just keep this in your mind, these three formula, and just create a tree diagram, and just you can figure out this. Okay, any other question?
Whatever is more likely to come in quiz 2.
Yes, sir.
Actually, so this is your doubt. Otherwise, I also collected the previous term revision session slides. So let me just open this and let me check if any new question is there. Or you can open join PD and you can see these questions. So maybe some question is already discussed, some is remaining. So I'm sending the chat box. So, 1 second. Yeah, first question. So have you joined?
Yes, sir.
So I've sent the link in chat. So this question, yeah. So I've just picked only the question from binary search onwards. Okay, so the maxi questions are not there. So what you should remember, what type of things you should remember for this? 1 second. Save on the monitor. Say pick.
Sir, predator means the previous one, no?
Yes. 1 second. Predecessor means just previous value in the in terms of the value in this question. Okay, so for this question, are you marking the answers? So consider the following binary search tree. Let indicates the name of nodes, not the value that are stored actually. What is the predecessor node in terms of value of M node? So for this type of question, you should know
Inline.
In order.
In order. In order.
Okay,
First
so
do in order, then see the predecessors.
yes, just apply the in order traversal on this, and okay, so after you will get the sorted order. So for the binary search tree, if you apply the in order traversal, you will always get the sorted order in increasing. So then you can easily find out the next node and previous node. So if where is the M? So M is here. So what is the predecessor, that means the just before this value. So what is the previous value just before this m? Okay, so I'm writing, I've already discussed this in order, pre-order, post-order in the weekly session. So if I apply the in order traversal, what order you will get? Can anyone tell me?
Sir, HO
H. Okay, so just
HOPID
LPR. Okay, so yeah, H, then O,
P
then yeah P, and then
ID
I, then D, then J.
JKEB,
Correct. E,
then
B, then
LF
L,
F
F,
M
then M,
N
N,
G
G,
A.
C.
Sir, after H there should be D, no?
After
I
H,
think.
H.
Yes, sir, it should be
No,
J.
no.
Left
Sir, in order is left root. Oh, sorry.
Yeah, left current root, so it should be HB.
H, D, and then O, sir.
Okay, okay. One second.
O, then I, then P.
Yes, sir.
Correct.
That is pre-order we have told, no, sir? No? Post-order.
Left, yeah, print and R. Yeah, correct. Yeah, I also missed. Yeah, so first move to the left. So H we are getting. Then we will come back. Then this node. Okay, so left is complete. Yeah, print this node. Okay, correct. D.
D.
And then we will move to O.
Y.
Then I. Then P.
Then B.
Then B.
Yeah.
B. Then
J.
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 Then
K.
A.
JEK
A.
A
Then A. Then L. Then F.
L F C
And C.
M
And
E
M.
M
G.
G.
N. Yeah, this is the in order traversal. Actually, we calculated the pre-order traversal previous.
Sir, there is always confusion in name, sir. Could you say some trick in order, pre-order, post-order?
So this is the small word formula. So left this LPR. Okay, this is for in order. That means left recursive call, then print, then right recursive call. So in the pre-order traversal, just pick this P as a first and LR. This is pre-order. Okay,
Sir,
and post-order.
pre-order P. Sir, what does P?
P means
P
print.
means current.
Print. Yeah, current node.
Present.
Okay.
Okay, L and R are the recursive call on the left child or right child. Okay, so P here I am writing for print current node. Okay, and for the post order traversal, L, R, N. Oh, sorry, not N, P. Yeah. Okay, so this print statement comes in between in the in order, comes at first in the pre-order, comes at the last in the post order.
Sir, P is parent or print?
No. Print statement, just print the current node.
Okay, I read somewhere
Okay.
it's parent, yeah.
Yeah, otherwise the remaining are left recursive and right recursive. Okay, so this is the...
So this is an easy way to remember. So for example, in a binary search tree, typically, if I've got 3 values, there's a left child, there's a root, and there's a right child. So the actual order is left child is the smallest. So in order always prints the actual sorted value. So it's very logical that left child will be printed first, then the root node, and then the right child. So LPR is the logical choice, right?
Yes.
But when it comes to pre-order, so that means the root node will be printed first, then both the children L and R.
Yes.
And if it is post-order, first you print the children, which is L and R, and then you do afterwards. So I think it's very logical. If we remember this, then I think there'll be no confusion.
Or you can also write the code for this. This code is also very small based on these 3 steps. If you are given as a binary search tree, you are given and root node is given, you can simply apply the in order traversal, pre-order, post-order by this only 3 steps, recursive steps. And you can see the order. Okay. So after just finding this order, just see that what is the predecessor of M, C. Okay. So this C will be the answer for this. Mhm.
So C is correct, right?
Yes, C is correct. Okay, second is also same. So this in this question, this is given traversal order. Which of the following order will be printed by the given code snipped? So I
Sir,
don't
this is
know.
left, right. So this is post order, no?
Uh, in my screen, the complete code is not visible, but I think this is left, right, and print. Okay,
Yes, sir.
so
Left, right, print.
print.
So this is post, no? Post order.
Yeah, post order.
No,
Yeah,
this
this
is
is post order.
pre-order. This is pre-order, no?
No, post order.
See, you look at when the root is printed. First, the children are printed, L and R. So then it is post. Parent
This
is
is the
coming at
case
the end.
L. This is the case L, R, and P. Okay, so you can see this is the only code required to traverse. This is the post order code. If binary search key is given and root node is given, you can simply write this small code to print the nodes in pre-order or post order. Just change the position of print statement, and you can write the code for each.
Sir, one previous year
Okay,
question, possible can you take, sir?
which question?
Sir, March 22, I am having a question. March 22.
Okay, so can you
Maths?
share your question?
Yes, sir, I will do that, sir. Sir, can you see, sir?
Mm-hmm. Okay, so some code is given. Match string. What is asking? Complexity.
No, sir, they are asking what does that code is doing with prefix, suffix, and all. They are given subsequence, substrings. Not able to
Huh.
understand.
Hmm.
If you can take,
So this is looking that this is divide and conquer approach.
yeah, by two is there.
Hmm. Okay, so for this type of question, just take a small example. As per the given problem statement, just take a small example and just apply the dry run according to this question, and see what type of output you are getting.
Okay, okay, sir.
Okay. So here actually we are asking that what this code is doing actually.
Yeah, as you told, its function mystery is an example of divide and conquer algorithm, and complexity
Huh.
also they are asking, sir.
Yes. So complexity is divide and conquer approach is given. Then what complexity is given in the answer? N
Yeah, N
into
into M,
M.
sir.
Hmm. That is actually here the value is given as a string form.
Sir, can you take
So
one
string is
screenshot of
also
this one, sir, if you want, so that we can all see.
okay. One second.
I will make it smaller.
No, just to increase the font. Just give me the code actually. Huh. Okay, one second.
Okay, sir.
Okay.
I'll stop sharing, sir.
Yes, yes. Oh, I need to read the problem statement. So what?
I will give one more, sir. Again, that problem statement I'll give you, sir.
Mhm.
Sir, this
No, not
terminology, what that, sir?
no. Above one.
That's also
This
nothing.
one, yeah. This one. One second. Consider the following function mystery array. Okay, so one second. This is also in copy. Okay.
You want this one's a terminology?
Oh, suffix value that I know.
Okay, sir. Then this is the what does the mystery function return that we can find out now.
Longest common prefix. Okay.
And I'll stop sharing, sir. And the complexity they're asking.
One second.
It looks like it's a dynamic programming problem, week 9 or 10.
No, no, divide and conquer problem. This is
Divide
my
and
screen is visible.
No, sir.
no, sir.
Okay, so let's see where
Sir, it takes some time, sir.
Yeah, now it's coming.
Now
Sir.
visible, sir.
Okay.
They're visible.
Okay, fine. Yeah, this actually middle part is inserted during the snapshot. Okay. My pen is not visible now.
Visible, sir.
Okay, so here the question is given. Consider the following function mystery. One array is given, and low and high index are given. Array is a list of strings, and low and high are the first and last index of list array respectively. Yeah. So list of strings are given. So okay, I'm just writing any string. So like a. Okay, like A, B, C, A, B, C, D. Okay. So just take some small this type of maybe 2 or 3 strings in the list. Then just call the function array low high. So if low, so low index is like first index. So this is 0, 1, 2, 3. So low and high return array low. Okay, so if this is the base case of this mystery, if low equal to high, okay, so that means we are simply comparing a case when we have only 2 strings. So like A and A. Okay, so if both are same, we are returning same A. But what happens? So in the main input, this is not the case. So if high is greater than low,
Sir, base case only one string will be there or 2 strings will be there, sir, in a list.
no, low and high is actually index. Okay, sorry. So 0, 1, 2, 3. So at any time, if we are getting only one element, so we will return the same. Okay, in this case. So low and high is representing the first index and last index. So we will call this mystery function every time we are reducing the size. So after reducing, we will reach at the case when we have only one element in the list. So that is actually the base case of this. Okay, and now the remaining part, the recursive call part, we are looking this high is greater than low. So high is the last index and low is the first index. So definitely the first, this condition is true in our input. So 3, so low is 0 and high is 3. Okay, so this is the condition true. Now mid equal to low plus high divided by 2. So we are simply calculating the mid element. So 0 plus 3 and floor division 2. So we are getting 1. Okay, and what is the one index? This. And we are simply calling the same algorithm 2 times. So mystery array low mid. Yeah, that means we are dividing the list into sub list like the merge sort. Okay, if you remember the merge, we are following the similar process. So we are dividing the list like this array and low mid. So first list we are passing A, and ABC. Okay, in next list we are passing, in the next call we are passing the next A, B, C,
+1.
D and A, B, C, D, these two. So now our problem is divided into two parts. So once again, the same function we are calling on the first left. So this is the first call. And now we have only two lists. So same thing, once again, high is, so this is now 0 and this is 1, 0 and 1. These are two separate problem now. Okay. So once again, AA and ABC, our high is greater than low. So once again, we will calculate the mid for this problem. So mid will become like 0 plus 1 low division 2, like 0. Okay. So that means once again, we will divide into sub problems. So now we are getting AA. Okay. And next is ABC. Similar for the second part. So A, B, C, D, and another is A, B, C, D. So this is the dividation part of the problems. Now finally we are getting this low equal to high. Okay, so you can see we have only one element. So 0, we have only one index. So this is the first index. This is the low value, and this is also a high value. So this is the base case of this algorithm. So in the base case algorithm, we are returning directly this str1. So str1, we are getting AA. Okay. So for this sub problem I'm talking about, this is one sub problem. We are getting str1 equal to AA. From second sub problem, we are getting str2 equal to ABC. Okay. And after getting these two value, we are calling the another function match, and we are passing this str1 and str2 in this function. Okay, so that means we are passing AA and ABC in the above function. Now we are coming on this sub
Sir, your
problem.
writing is not visible, sir.
A bit of lag.
Please.
I don't know why this lag happens sometimes. So this part is okay. We first divide the problem.
Yes, sir.
Divide the problem. After reaching at the base level, we are returning directly strings from the single element, and we are getting str1 equal to AA, str2 equal to ABC from these two sub problems. Okay, and we are calling the remaining third function match str1 str2. So that means we are passing this AA and ABC into the above function. So in this function, so here AA and ABC, we are passing into this. Now you can see the result equal to this empty. N1 and N2 are the length of both. So we will get N1 equal to 2 and 2 equal to 3. And I and j are set to the 0, 0. While I is less than N1 and j is less than N2, we are simply comparing the string here. Okay, in the loop we are, when I is less than n1 and j is less than n2. This is also similar type of approach of the merge algorithm of the merge sort. Okay, so here we are comparing element one by one. So stri does not equal to str2, we will break. Otherwise we will simply store result plus equal to stri. So you can see we will we are simply comparison the character by character. So if A and A is matched, we are storing inside the result. Result equal to A in the first. Now we will move to the next character. Okay. So this is not matched. In this case, we will break the loop. Okay. We will break the loop and we will return the result. So that means what we are returning from this algorithm, prefix, which are common.
Oh,
Okay.
okay.
Which are common. So A and A is matched in two strings. We are returning into back.
So
So
common substring between two. If we have two elements, what is the common substring between these two?
So in this sub problem, we are returning this only common prefix in the two strings. But if you combine this in the all, so that means actually our main operation is we are returning the common prefix in all over all strings. Okay, so after getting the result of this first two, we are getting A. Okay, now our next operation is performing on this. So similar to from this side. Okay, so from this side A, B, C, D, we will get what is the common from this side is also A. Okay, now we will apply the match on this A. We will get A. Okay, so finally we are getting the common prefix strings in all strings of the list. So this is the working of this algorithm. So we are finding the common prefix, and if you see the complexity things, so how we are getting the complexity. So first thing, here actually we have strings. Okay, so this is not two single, this is two strings actually. Okay, and string is also have some size, so the length may be anything. So is any so in the second question, just check that if any information is given about the length of strings, what is n and what is m.
Sir, longest, which are the following is true about the mystery function? Assume the size of the input list is n. Input
Huh.
list n.
Huh.
Length of longest string in the list is m.
Okay. Yeah. So list size is n. That means we have total n strings. Okay. But every string is actually m size.
Or the longest is m, sir.
Or longest is m. Okay. So that is actually we are processing n list. Okay, so if we consider only single element, like the merge sort. So that means we have the case like n log n case. But here actually we have the every string, maybe the size is m, longest size is m. So we are comparing the string inside this process. Okay, inside this process we are comparing one by one. So this loop is running m time internally. So while this inside this n1 and n2.
But that's a order one task.
Not
Means
order one. How it will become order one? It will
it's a
become order
Actually,
m.
go to m, up to m, sir.
Yeah, because it's a linear search. Yeah.
We are comparing one by one.
One by
If
one, m.
any size is m, so it will become a order of m.
Order n, yes.
And mystery will be n log n, no, sir?
No. So yeah, so this time n is the list size, but m is the string size. It is not. We cannot write in that way. So m is, if we write the recurrence relation for this, so tn equal to 2t or n by 2. We are dividing the size of list. Okay,
plus
but this will remain order of m.
m.
Okay, so this m will not change actually.
So here the f is m basically.
Sir, again 2 n by 2 is n log n, no, sir? Equal. So n log n plus m will be there. Sir, your writing is not visible if you are writing something.
Yeah, there's a lag. Let's wait another 5 seconds.
Yes, sir. O of m, okay.
O of m actually, and this m is not depend on the
n length of the
this
list.
n by 2. So if you see this,
what is m?
Write size of this strings. Okay, this time is required based on the string comparison. Okay, that is not depend on the input, our input. This is totally independent. So if we just draw this, so tn, okay, and we are getting tn by 2. Okay, tn by 2. But here we are getting m. But in the next case, we will also get m from here and m from here. Okay, then it become 2m. The next case.
So this is a case of increasing.
n by 4. Let's say Tn by 4 and Tn by 4 like this. Okay. So this will become 2 to the power 2m. This is 1 to the power 0. This is increasing case.
So
Okay.
n to the
So
power
in
of
this
log
case,
CR.
n to the power log
CR.
CR. Okay, but we cannot.
Regression speed 2.
No, but in this case, actually,
You should put M, sir, here, otherwise. M.
no, actually, this is not the. This is different case. Okay, 1 second. What we are doing? And this is increasing. Totally independent.
Sir, actually 2t n by 2 will give n, sir. If you don't consider this one, 2t n by 2, as we already did there, it gives n. And then for every regression, there will be order of m, no, sir? So you have to multiply that. Is it something?
1 second. What we are getting? No, from this. So if we are writing m log CR, what C value we are getting here? 2, 2. 2, 2. This will become 1. So we will get m this case. But we have to look again. Code. Okay. So str1, str2, we are getting two strings and combining by then combining the size. We are selecting the prefix part. So some piece this is size. So this is two strings. We are getting one string. One strings. Equal to a strings. So every time we will get two string in the input prefix. A case. This is also two case. So this is constant. We are always picking two, and we are selecting. We are getting one, then two, one, three. So M comparison, M login. Yeah, I think. Yeah, correct. M login. This is looking like M login should be the answer for this. Maybe we have re-evaluated this in the previous term. Okay, so MN is not looking correct. M login is looking okay.
So here the equivalent of merge. So what you have done typically in a merge set, we have the merge operation, right? So here we have basically written a different merge. Instead of writing the typical merge, we are doing the match. So
Yes.
there in the merge operation, we are picking just a max of 2, so order 1. Here, because we are doing a string operation, that's a order M.
Order
That's the
M.
only difference between this problem and the merge set problem.
Yes, correct.
So right, rest of the thing will remain the same. So wherever in the merge set we had order 1, and then we just have to substitute that with order M. The rest of the process remains the same.
But actually, in the answer is given n into m. So I'm not sure this question was re-evaluated in the term.
I think sometimes there are typo in the answer key also,
Yeah.
right? So you have to think it fundamentally, right? What's going
Sir,
on?
I'll now put it in the discourse. So future we can correct it, sir. If at
No,
all
no
it is.
need to no need to put on the discourse. We all if we use the previous questions, so we always review, and professor is also reviewed.
Hopefully this is not on Sunday quiz. Otherwise you are good.
Okay. Otherwise, this is divide and conquer approach, and your solution is this little bit tricky for this, because here this m is totally independent of this n. Okay, and every time we are dividing 2, but we will
So if it's
always
independent, then why are we adding it multiple times? Shouldn't the thing be at each step?
so for this part actually, string comparison will take m time. So this is not dependent on n by 2. Okay, and this part also it will take m time, because every time we are passing 2 string.
So but that m size is not the constant, right? The string size is also reducing.
Not reducing. So what is the case? Suppose if every string is equal,
Even if it is
like
equal,
a like this.
so but we are still dividing the string, right?
No, we are not dividing
No.
the string. We are dividing the list.
Okay.
Okay, suppose this is a list. Okay, we are dividing into 2 lists, and then once again we are dividing into 2 lists. So we are getting finally one strings. A. Okay, and
Yes.
again a.
I'm not dividing the string, is it?
Yes,
We are comparing the string.
like this.
String 1, string 2. A,
So finally we are getting
0.
this, and we are passing two string into a match function, and match function is returning a common prefix. Okay, now in this case the complete string is matched. So in output you will get one string a here. Okay, same here.
Sir, if we again, this is again an adaptation of merge sort, right? If we kind of look at the merge sort, right? There are two operations, sort operation and merge operation, right? So sort operation, we know it's actually n log n order. Merge operation is order n, because we are doing, n merging. So if we do now there, we are doing n merge with, each operation was order 1. So that's why we got order n. Here, the operation is order m. So if we do that, then I think we'll get our answer. Because there, between n log n and order n log n was a sort operation was more expensive, so our time complexity was n log n. Here we are comparing, when we talk, let's say this mystery operation is equivalent to our merge operation, right? And the other function is basically
but actually merge operation here is not dependent on n. So suppose in the first case we are getting only one merge here. Okay, not merge, not a simple common prefix. So time is at this place is required m. Okay, and only one operation. But here actually this process we are receiving 2 strings before from the below. So it will also take m time, and this will also take m time. So both are separate. So we are getting 2m here. 2m process. Next level we are getting 4m process. Now we need to identify our complexity based on this information. If our m is increasing, okay, and how many levels we have? We have only log n level.
So m into log n must be the answer, no, sir?
M into log n is looking correct.
Yeah, because even similar question was asked in the next quiz also. Similar, like mystery algorithm, something they have given, and they are asking for the similar. What does the mystery
So
return?
it's
And what is there is 4-mark question, another 4-mark question. What is the time complexity? After giving the function. So you can expect this type of question also in our quiz.
Yeah. So it's a divide and conquer. So in the case of divide, what is the thing, and then conquer is where we are doing merging, right? So we are dividing the problem into sub problem, and then we are merging it intelligently, so that way we get the answer, right? So these two components, complexity, and then we multiply.
Sir, you wrote the expression for this, right?
T of 2n by
Yeah.
2.
So if it's increasing, it will be that case, right? Ki, n
So
or
2 to
log
the power
r
0 m plus
base.
2 to the power this 1 m plus 2 to the power 2 m, and finally we will get 2 to the power log n into m. This is correct. So number of operation we are getting in that way. To the power 0 to the power 1 to the power 2 like this. This 2 is increasing in this way.
The last term is nm.
So m is common in this. So what output we will get? 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 to the power log n.
Last term is nm, no? Sir,
So
largest term.
Sir, like this is the increasing case, right? So you said the complexity is going to be O n.
Okay. Yeah. So this
Yes, sir.
common is this m is common, and if we see the case of the terms of n, so this part is actually increasing.
So it will be mn only.
This part is increasing. So so what complexity we will write? N into
N into m.
log
No.
C.
2 power.
So
2 to the base 2.
it will, we are got
तो nm ही होगा फिर
so that is we are getting n into m. Yes, so this is a little bit tricky.
Pray God that such question will not come this term.
It will come. Murphy's law.
Yeah, actually this increasing and decreasing we always see for the input actually what we are giving this n. So how we are dividing? So we are dividing this input list actually. So we will see how it is increasing or decreasing. So this sequence, this part is common every time, but this part is depend on the input.
That log CR.
Sir, what was the recurrence relation actually?
The 2 by 2t 2 times t of n by 2 will give only n. Okay, that's what you have written. N into m. Okay.
Recurrence relation is Tn 2t n by 2 plus
2t n by 2 is actually equal, no, sir?
This is equal case.
2 to n by 2 is equal. So equal case is log
No,
n.
this is not the case.
This is
Actually, every time this operation is increasing, na? So every time in the initial case we are getting m, next time 2m, and then 4m. Okay, so this
m you are
m is
separating
common.
out. Okay.
But this series we are getting like this 2 0 plus 2 1 plus 2 2 and then 2 log n, because height will reach at the log n. Okay, so we are calculating the separately for solution for this part.
Okay, now I can understand something. Okay, sir.
Renji, you are asking very good questions.
No, it was there in the question paper.
Okay, so just quickly go through the our question. So this is in order traversal, so I think not much difficult. And okay, so if binary search tree is given, okay, and we are performing in order traversal or pre-order traversal or post-order traversal, so what would be the complexity if our tree is balanced or not balanced?
Whether tree is balanced or not, it should be n only, no, sir. Traversal to go for all the nodes it has to go. So O of n.
Yes, correct. So we are performing traversal operation. So traversal means we are traversing each node. We have n node. So if our tree is balanced and not balanced, so it doesn't matter. Our algorithm will traverse all the nodes. So complexity will remain order of n in both cases.
I think this is basically search versus traversal. Traversal will go through everything. Search is, you just the path.
Search is different. So if balance, then you will get worst case is log n. If not balance, the worst case is total number of nodes. Order of n. Yes. So consider the binary search tree of height h. Which of the following statements are true?
The number of elements in H is at least H because height. At most,
Yeah.
it is wrong, sir. Number of elements in tree is at least 2 is wrong. 2H wrong. Number of elements tree is at most. That is the maximum number of elements we are having now, sir. 2H, 2 to the power H minus 1.
Yeah, so this is actually first term question. So,
Sir,
but
this one is problem, sir. Root node is considered at height 1 and 0, sir.
yeah, that I'm actually telling now. So after first term, actually we found this type of confusion. So after that, we always add this condition. So what height or we are taking for the empty list, that things. Okay, so base case we always define in the questions. Okay, in this question this is not defined. So just consider that the if there is one node, the height is 1.
That means if it is only one root, singleton set, height is 1.
Yes.
So option D will be correct here, right?
The option D will be correct. The number of elements in the tree at most H.
At least H, no, sir.
At least H, yeah. At least correct.
At most means you can have
B
any.
correct. B correct. D correct. And just E is not correct. So just see the F option. This is also a question
Number of nodes is 0 shall not
we
be
just
n.
discussed.
Number of nodes 2 shall not be n equal n plus 1 is always true.
This is also one property of Anis's tree. Or you can just verify by some example. Okay, if binary search is given, binary search tree is given if the number of nodes with 0 childs n0 and the number of nodes with 2 childs nodes are n2, then n0 will always be n2 plus 1. So I'm creating one child like this. So you can see in this diagram. So two child nodes are 1, 2, 3, 3. Okay, so n2 equal to 3, and leaf node you can see 4. So leaf node you will always get n0 will always get n2 plus 1. Okay, so this is also one property of binary search tree. You will always get this situation.
How can we prove it, sir?
For proving, okay. So suppose we have n nodes. We have number of nodes are n. Okay, so one equation we can map like this. So we can write in that way. So n2 plus n1 plus n0 will equal to n. Correct?
Yes, yes.
Okay. And another condition. Let me check.
Edges.
It will be n, sir. 2 children. N2 will have more sometimes, no, sir. Not required.
No. This is correct or not? This expression.
Yeah, basically there are leaf nodes or
No,
Leaf
it
node or
cannot be
one
right, sir.
child node or two node child. Total.
So it cannot. It is not right, no, sir. So because your
Why?
root node is also having 2, and below that also will be 2. 1, 2, 3. Oh, okay.
Okay, here we are just talking about the number of nodes. So number of nodes which have 2 child, number of nodes which have 1 child, number of nodes which have 0 childs. If we add all the nodes, we are getting total number of nodes.
Yes, correct.
Correct. And
Okay.
number of edge,
2 and 2, 2 and 2 plus
n minus 1. If we are writing simple, number of edge equal to n minus 1. This is okay?
Yes.
In the binary search tree. If we talk about, if we now just calculate the number of edges from the above equation,
2 and 2 plus n1
huh,
equal to n
2,
minus
2 into, so
n2
this n2, yeah, n2
plus
plus
n1 plus
n1
equal to n
plus,
minus 1.
so this,
Zero.
yeah, this is not creating
Zero.
anything, okay,
Zero.
yeah, equal to n minus 1, okay, and okay, so n minus 1 we are getting, okay,
So you take
ha
the
ha ha
left.
ha ha ha.
So then
So
you take
it,
N1 to the other side and bring
then we will just put the above, okay, so just write this n2 plus n1 plus n0 equal to 2 n2 plus n1, and this one we plus shift here, so plus 1, n1 plus 1. So here actually we just mentioned two equations. So first equation is this one, and second equation we will get from here 2 n2 plus n1 plus 1 equal to n. Okay, so both are n, and then we will combine this. So this n1 will drop. Okay, now from 2 n2, so we will
One and two.
subtract this n2. Okay, and this part. Okay, so n0 minus 1. We are getting the relation. Okay, so we can write n0 equal to n2 plus 1. Okay, so this is one property. Yeah.
this is
Okay,
awesome. Thank you very much.
correct. Now, any confusion in this?
Properties of BST, sir.
Binary search tree. Or binary search tree or binary tree. Okay,
Binary.
binary tree also. So binary search tree is also a binary tree actually. Okay,
Binary
but
search tree, the only condition is your numbers will be
yes, order is
left side
given
and right
actually.
side.
Order is given, but okay. So this is the one question, and next one is, yeah, this type of ordering question. I think you have already solved. We have given. Oh, this is not given now in anywhere. So this question you can simply just draw the lines, and just check that if any line is overlapping, then just not consider that. One second. Yes, Ritik.
No, sir. Sorry, sir. Actually, I mishap.
Mhm. Okay. So this question you can simply solve by just draw the line. So AS. Okay. So AS is starting from the first. Okay, and S means start and E means end. So if AS is start, okay, so you can just draw the line. This you don't know where is the ending. Okay, so one room is required to perform this. I think room is asking, yeah, room. Okay, and after that second activities also start. Okay, so you can see you need the second room because you don't know this time. At this time you don't know S is complete or not, so you have to perform the second. So B, so this is first room, you have to assign second room for B. Okay, and this activity is also running this time. When you are reaching at C, still you don't know A is complete or B is not complete or not, so you will need another room for C. Okay, so C activities now start, but in the next time A is complete. Okay, so this room is empty.
So D can start.
So if this A is complete, you can use the room. So D, you can use the D here. Okay, now D is running, and C, yeah. So C is end now. So
So E
this
can
is
start.
also complete. Okay, ES, yeah. So you can use the C room for E. Okay, now E is running, and then BE complete. So B is complete,
F.
and F is start. So F you can use here. And D, yeah, now all are running. Okay, so D F, E. Okay, so D is complete. Now D is complete. And G. Yeah, so G is a start, so G will use this first room. And then E, yeah, E is complete. Then H is a start, so H will use this. Okay, then now F, yeah, F is complete. Now G is complete and H is complete.
Three.
So you can see only 3 rooms is required to perform all this activity. Okay, so this is the one solution. And Hopman, we have already discussed this. So how many bits will be used to encode the message A, B, C, D, E? So just create a Hopman tree for this, identify the length of each code, and then just apply the length of A plus length of B plus length of C plus length of D plus length of E. Okay, to get this answer. So I think this can be solved.
Sir, the process is simple, no? Just we have to sort it in order and then we need to choose the two child which are the minimum.
So just tell me which will we select first.
The first selected will be E and C. E will be on left side and C will be on right side.
It doesn't matter, yeah. So still, if you want to maintain order, E and C, correct?
Yeah.
And you are getting 16 and
We can
11. So
sort it to 16 and 11 also.
1
So
6
6.
and this 2 7. Okay, 2 7.
Yes, sir.
And next, which will
2 2 and 2 1.
Yeah, that one. Okay, so that will select the separately. So
A and B, sir.
So B and A.
It will be 43.
43. Now next one is 30 and
Next one is
27.
31 and 27.
Yeah, so this
So
30.
BC will be one side and D will be another side.
57. Yeah, now that this is the final one. Okay, so 100. Okay, anything is remaining?
3 bits.
Yeah, all are done. So for A, we need 1 2. Okay, so 2 bits is required for A. B, we need 2. And C, where is C? This one. Okay, so 3. And D, D is 30. Okay, so this is D. So D is 2. And E,
3.
3. So total is 2 plus 2 plus 3 plus 2 plus 3. So 6 plus 6 is 12. 12 is answer for this. Okay.
Okay.
Just we have to sum up or everything. So 4 plus 3, 7 plus 2, 9 plus, oh, sorry, yeah, 12, sorry about that.
Okay, so move to the next. So inserting binary search tree, you should know how to create a binary search tree for the given order. Okay, so and the here asking that the element at maximum depth. Okay, so you can simply create a binary search tree for this. So simply
Sir,
add
we will
50.
also balance along
No,
with
this
that.
in no. Here we are asking that to create a binary search tree. Do not balance for this. If the question mentioned is that create a AVL tree, then just apply the rotations. Okay, so 80 will insert here.
Okay. Means if we say AVL tree or either it's a balanced binary tree.
Then apply the rotations.
So AVL and balanced binary tree are same, no?
Yes. Otherwise, to create a balanced tree, there are another method are also available. That is not the similar things. A
So AVL is
balanced.
one type of balance tree.
So actually, AVL method is create a balanced binary tree.
Sir, almost balanced because there is a plus.
Almost balanced.
Almost,
Yes.
it's never, you can't say 100% that it's perfectly balanced. There is a chance it could be slightly left can be
So
more.
only difference is possible the one height.
One, yes.
And the other method are also available like red black tree, but that is not the part of the course. Okay, so this 80 is added on the right. 20 is smaller than 50. Will add here. 60 is greater than 50, less than 80. Will add here. 10 is smaller than 50, smaller than 20. Connected here. And 45 is smaller than 50, greater than 20. 45 will add here. Then 65 is greater than 50, smaller than 80, greater than 60. 65 will add here. 30 is smaller than 50, greater than 20, smaller than 45. 30 will add here. 90, yeah, 90 is greater than 50, greater than 80. 90. Okay, so what are the elements which are at maximum depth? So 30,
30, 65.
65. Okay, so 30 and 65 is the answer for this. Okay, so this is AVL tree properties. So AVL tree is also a binary search tree. So you can apply the binary search tree some property like this. If the height of AVL tree is h, the maximum number of nodes will be. So if so, maximum number of nodes is possible when your tree is completely full. Okay, at on each level. So that is the case when you are getting. So this type of condition we always mention that here this is mentioned that assume that the height of the empty tree is 0. Okay, so just
So in
convert
the
your
first
formula.
condition, it should be plus one, right? SH minus one plus one. It's negative or plus?
Okay, 1 second.
Plus,
Oh, that should be +1, I think. Yeah.
Yeah, there should be plus
wrong.
one. So maybe it's a wrong answer. Maybe
Wrong answer. Yeah, correct.
yeah, because it's actually plus one. The plus one is the correct answer.
I also forget that this is a question.
That's what I'm saying. Is it typo or is it actually?
No, no, this is wrong. Yeah, this option is wrong. So this should be +1. S h minus 1 h plus s h minus 2 plus 1. Okay, so this first
Sir, which
option
one
is
you are telling, sir? Could you please write that
option
again?
A. So option A is incorrect because correct height formula this number of nodes formula is S
1
H
plus 1
minus
plus previous one and previous one, right?
S H minus 2 plus 1. This should be
So
plus
that
1.
is okay, no?
No, this is
Okay,
given as a
minus.
-1. Yeah, because of that this is incorrect.
S0 is 0 and S1 is 1. Okay.
This is okay.
Height of 0 is 1. Okay, okay. So here we are defining height of 1 is 1, right?
Yes. So second property in aerial tree, the absolute difference between the height of left subtree and right subtree of any nodes can't be more than 1.
Yes, sir. True. 1 can
Yeah,
be
this
or
is
0 can be. Log n is also true.
this searching time is log n. This is okay. If the height of aerial tree is s, the maximum number of nodes is this is also okay. The complexity of both insertion and deletion in aerial tree is order of n.
Sir, it is
This
log
is
n, no?
log n. Yeah. Okay. So insertion and deletion also
Sir,
is
instead of if it will be binary, then what will be our answer? First will be incorrect, right?
hmm,
And the second one does not make any sense. The third one will be incorrect. It will not be always sometime.
yeah, incorrect. Yeah,
And
so maximum number of nodes are correct.
the D option will be correct. That is the minimum, right?
No, D option for the binary tree, the maximum number of nodes are possible only 2 to the power h minus 1. This is correct.
Okay, okay, maximum number. Okay, right. And the last option will be may or may not be worst case, sir, right?
Yes, worst case will be order of n.
Because if the string is ascending sequence, so it will be height of the tree will be the number of elements. So
It's
we are
not
inserting.
in AVL tree, if you
AVL
insert
is
or
log n,
delete,
right?
we also
And
have
sir,
to
best
follow
case will be log n, sir, right? Last.
Yeah, best case is log n.
the complexity of insertion and deletion in AVL tree.
Hmm.
I mean, it is like, I mean, what I want to say is that.
So AVL tree, finally we get the balanced tree and the height is possible is log n. Okay. And for the insertion, you have to traverse the complete height. Okay, then you need to add the new node. So that means that you have to traverse all the height. So height is log n. So insertion operation is required, log n operation.
So maybe
But
the
to
best way to
balance, we don't require additional to balance the tree.
No, that is balance. So balance it also takes only maybe one rotation. So maybe one rotations or two rotations. So that is also a constant time. So that not affect the overall complexity.
So the last option is incorrect, right?
And last option is incorrect in this example.
So the reason why we did all these left-right rotation business to guarantee that the tree is balanced and will achieve the best efficiency in terms of
Yeah,
search.
each operation. So this
Sir,
insertion,
the
searching,
method
deletion.
that we have taught, the balancing left-right rotation, will it always work, and is it the best way to make the balance tree, or there is other better way to make balance tree?
No,
Means this
AVL will always work. AVL method, this rotations is given, that will always work. So because of
means
that, this is the standard algorithm.
means for all cases it will produce best solution, right?
Huh. Yeah, according to the condition which we are following in this. So after getting that this balance factor 2 greater than 1, we are applying the rotation to maintain this. So we will always get final binary search tree where we will approx get the log n height.
Okay, sir. Next question. Sir,
One
19
thing was
questions
not
are
covered,
there.
which was covered in DBMS is the B minus tree, B
B
tree.
tree, B tree.
Yeah, I know we have not covered here. It's DBMS. That's
Yes.
much better actually.
There is one data type B tree, then B plus tree,
Yes,
and for balancing there is one RB tree,
red black.
red black tree. Yeah.
Yes.
Some topics
Sir,
are not covered in this
sir, why
course.
PDSA is not in two terms, sir? PDSA part 1, part 2, sir.
In NPTEL, actually, this course is running in the two separate course.
Yes,
Every
sir.
One is the PDSA course, that is 8B course, and another is design and algorithm analysis course, and both are running by the Professor Madhavan Mukund sir.
He is mathematic professor, but always teaches come DSA.
Yeah. Okay, so next one is this is AVL tree. We have already discussed. First, create the AVL tree. So for this 8, simply we can create like 8, no problem. Then 4, this is also not creating anything. So this is 1. So after this, we will applying the rotation, and then we will get like this. 4,
It's not visible, sir.
not visible.
Now it is visible.
Now it's okay.
So we are inserting 8. So 8 will not the 8 is not the unbalanced. Then we will insert 4. 4 is also not unbalanced. When we are inserting 1, so we are getting 0, 1, 2. Then we will apply the rotations. Now we will insert 3 in this. So 3 will insert 3 is less than 4, greater than 3 here. Okay, so 3 will insert here. So 0, 1, 0, 1. Okay, so not well unbalanced. Now 9 will insert here. So it is also not 1 or 0. Okay, and then we are inserting 2. So 2 will insert here. Okay, now it is unbalanced. So 0, 1, 2, and 1, 2, 3, and 1 here. Okay, so this is now 2. So in this, so this is the RL case. So RL case we will apply 2 rotations. So 4, 1, 8, and 9 will remain as it is. But now this will become 2 and 3. Okay, and we will apply one more rotation on this. So this will become 2, this is 1, this is 3, this is 8, this is 9. Okay, now this is balance. And when we add 11, so 11 will add on this side. Okay, so now this is unbalanced, 0, 1, 2, and this is 0, 0, 0, and this is 1. So we will.
Sir, how you have rotated after the third part? Sir, 3 will be at top, no? This is
No,
right to left.
first rotation we will. So this is RL case. Okay, first rotation we will apply on this 3. Okay, so this will rotate clockwise.
Sir,
So we are getting this.
wait, sir. At one there is unbalanced, no?
One unbalanced, yes.
So one,
So
so you will first rotate three, no? Three to the top. Oh,
no,
sorry.
this is
At
RL
three.
case.
First child of one.
Okay,
Ha,
first I need to child. Okay, first I
yes.
will
First
child
rotation we
rotate.
will apply on the child. This is clockwise. Then we will apply the next rotation anti-clockwise
So
here
two
on
will
this
be
one.
at the top.
Yeah, okay. So after inserting 11, we are getting unbalanced here 8. Okay,
RR.
so this is RR case. So RR we will simply apply one rotation.
At eight, at
Ha,
eight we will
ha.
apply.
So 2, 1, 3, and then 9, then 8,
8 and 8.
and then 11. So this what we're getting 1, 3, 8, 11. First option. Okay.
All right, sir.
So
Ha.
now ideal tree is becoming very familiar. Rotations, everything, I think 3, 4 days there was a bit doubt in the
Yeah.
session.
So just applies just solve 3, 4 example for yourself. Then it will be easy for you.
And sir, while lectures are not updating, sir, after 2 year, I think have been gone. Sir
Professor
recorded,
lecture.
recorded lecture, professor lecture, yes, sir.
Any updation is required?
Yes, sir. NPTEL condition says only 4 terms, one lecture can be there.
No, I
Means,
don't know.
sir, new
NPTEL
student
is
are
lecture
coming,
is also
sir.
not updated.
Sir, but new student are coming. They will be disappointed that 2 year back lecture we are studying.
So topic are same. So algorithms will remain same. So what need to be changed
Any
in the
new
lecture?
technology, then it's fine. But if it's like basic maths and concepts, so I don't.
If any new topic is required to involve, then new lecture will recorded.
But sir, many means if it will recorded again, then maybe explanation will be better. Maybe from other
Sir, I have
teachers.
heard.
Madhavan sir as teaches the mathematics. Maybe other professor recorded and give an option. You can watch anyone. Means in foundation, sir, there are some subject that we don't like the lectures.
Ritik ji, quiz two revision is over, huh?
Okay, so some questions are also remaining. So here this question number 10. Okay, so in this question, we are asking that which Hoopman codes are valid code. So
One is not. A,
codes are given. Just identify that which codes are invalid.
A is invalid because C and D are having the same starting.
C and D.
C and D are having 0
Zero
code.
one common, yeah, that's dangerous. Yeah. Can't
So yeah, so in this type of question, just see the prefix things. So if any code is prefix of another codes, so that is not a valid code. Okay, so the 01 is coming at the prefix of C code. So this is invalid. It cannot be generated through the Hoopman codes. So in that way, just see every codes. So 000. So this 01 is coming
C,
at this.
C is invalid. C is invalid.
So B is valid or not?
B is valid.
B is looking correct. Yeah, C is invalid because 101.
100
Yeah, 101 is coming at here, and also
100.
100 is also coming here. That is invalid. Okay, and the remaining is 00.
Sir, D is also invalid.
Why?
This is
Sir,
valid.
B 01, then C 01.
0, 010 and 011.
No, both are
Yeah,
different, no?
but 01, right?
No, just see the complete code.
Okay.
Just see that if any character complete code is coming at as a prefix on another,
Mm-hmm.
not the
The
partial.
D
Okay,
is
so
not visible. Can you please scroll it up?
that is not scrollable actually. So the some things is
This is
coming
valid,
on.
sir. D is actually valid. Another way is to also draw the tree. You can see.
C D is valid actually.
B and D are valid.
Can you make it visible, sir?
Actually, I was also not able to see. So this is
This is
A0.
okay. This is okay. Just leave it. Yeah.
A00 and 010. So 0. So no code is prefix of another. You can see.
Sir,
So
any shortcut way for checking prefix? Means if
so
it there
simple.
20 character.
1 second. Simple. Pick the small code and see in the larger one. Okay, so just see this 11. So 11 is coming on the any other bigger code. Okay, 10 and then 11.
So the question we solved,
And
right? The common
and
prefix.
after that three letters, right? 2, then 3, then 4, right?
Yes. So you also no need to check for the larger one because that is cannot be. It either be exact same but cannot be with the prefix.
So that mystery match problem that we solved, right? This is actually the match problem.
In week 9, we will see this prefix or suffix type of problems in the dynamic programming. And I think week 9 is already released. Have you seen the content?
Yeah, yeah.
That type of problems will come. Okay.
Next question.
1 second. So next one is, yeah, this is we have already solved. I think this is also similar to the mock question.
Yes, sir.
Need to discuss? No, I think no.
No, sir.
Sir, we will first sort by earliest finish time, no?
Yes, finish it.
Okay.
This is also.
This is also in the mock.
Sir, please solve this one, sir.
So here this is the formula based directly. Okay, so what are the maximum possible?
And minus 1 by
0.
So size is 15. So if size is 15, so 15. Sorry, how this is increasing?
15
n into n minus 1 by 2.
105.
I'll reduce the size.
So maximum number means NC2 directly we can say, right?
So 15 into 14 divided by 2. That will be the answer.
Same
And what will be minimum number of pairs? That will be 0?
0. If our list is already sorted in increasing order, then 0. Okay.
Okay, sir, got it.
And this is MOM based. When we
Sir,
are using
MOM.
this median of medians, this algorithm will indicate median of medians.
It's order and
First is right.
Using MOM, the worst case running time of the to find the kth largest will be order of n. Big of n. First is correct. Second is not correct. The opposite. Okay, n log n is not correct.
Third is right.
Third is quick sort. Yeah,
Yes,
quick
sir,
sort is
third is
also
correct.
improved by n
1
log
and 3.
n. Yeah, so 1 and
So
3.
1 and 3.
Yeah, correct.
In this context, one question, sir, small question. The worst case running time for quick sort normally is n square. And now we are saying by using MOM, n log n.
Yes.
But apart from everything, forget everything. Somebody says, what is the worst case running time for quick start? So why shouldn't I tell it as n log n?
Because your pivot is chosen badly, right? So
No. The question is, what is the worst case running time for quick sort? That's all. Whether MOM is using or not using it as a programmer,
It will
my
be n
issue.
square, no?
n square. If your pivot is always the first element.
No, sir, you are not understanding my question. I think.
But
Other thing is
if this
understood.
thing is not mentioned clearly in the question that MOM we are using MOM,
No, sir.
then
But we
we are talking about the standard algorithm, basic algorithm.
But
No,
when we
what
can
I am
use
asking is in a real life situation, just like that, quick sort, if I want to do quick sort algorithm, I can do it in n log n, no, sir. Whether I am using MOM or not using MOM, what is the we can do quick sort in n log n time.
No. So if you are not using MOM, then worst case is n square.
But we
Yes.
will always use the MOM, right, sir? We can always use the MOM.
So that is actually first. So this is the process of create development of the algorithms. Okay, so first quicksort is developed.
Actually,
Okay, so at
maybe
that time,
then pivot is defined how you choose the pivot. Quick
huh.
sort. If you want in general question, maybe pivot must be given. That what you have chosen.
No, in the all the case, if you are selecting pivot as a first element, you will get the worst case n square. If you are selecting pivot element as a last element, still you are getting order of n square. If you are selecting randomly from
Then
any
also n
port,
square.
then is also n square.
But if we are selecting MOM, then it will be n log n.
Because MOM is providing uh, this guarantee too that after selecting the pivot will always come in between,
So why we
not
are
in the corner.
not using MOM always, sir? Why not? Why we are not using MOM always?
No, you can use always. Who is restricting on you?
No, but you are telling no, sir. Quicksort is n square. So when I use always, it becomes n log n. No.
Yeah, so that things you have if it is specified that because the first quicksort developed without the MOM.
But I think
Okay,
N
so this
square is
MOM
very
is
rare.
developed later.
I
Yes,
think
sir.
N square is very rare.
Today, what is the position, sir? Today it is developed, and I am without saying it as MOM. That 4 lines of code I am adding into the sorting
So you
method.
can just tell me. You can simply mention that the quicksort complexity is n log n if we are using MOM.
So that if
Maybe you want to say what is worst case. If that is given, then I think n square will be better answer because it is asking worst case.
No, worst case if you are using MOM, still now the worst case will improve in the quicksort.
Yeah, the correct way to ask question will always give the pivot. How you choose the pivot.
no,
But
correct
if
way of asking you cannot say no. So I am asking simply. I am asking.
yeah, if you are directly asking, then it is incorrect question. Either we can say it is incorrect way, or if you consider then also then from common sense you may say that quicksort may go up to n square. If you randomly choose any quicksort algorithm, so worst case will go n square.
No, if this type of question is asked anywhere, if this things is not mentioned that MOM is used or not used, so that means the question is asking related to the basic or standard quicksort algorithm.
Yes, sir. Now I understood. N square will be the answer. Even Google, when you search simply as quicksort, it says n square
Yes.
only.
So that is talking about the standard algorithm, quicksort algorithm. So this is the some additional things. We are improving the quicksort. But when we are talking about simple quicksort, so we will get the answer answer
So we should
always.
give
Yeah,
a
I
different
think it was
name to
covered
that,
now.
sir. Actually, we should differentiate the name then.
Huh. So one advanced quicksort is named by the randomized quicksort.
Randomized quicksort.
So in which actually we pick the pivot element randomly. So
So
that reduce the chance of worst case actually,
Sir, is there
but
any
not
better
guaranteed that.
sorting algorithm which
Mm,
computer uses best sorting the
no,
names?
actually this Python is also sort. Some name is
Team sort. It uses team
team
sort,
sort,
combination of
and that is
insertion
also a
sort.
combination of insertion and merge sort.
Some of them merge sort, yeah.
but the best
What select they are naming quick select and fast select. When we are using MOM, they are naming it as fast select. For
No, naming is actually no, select is different. Okay, so quick sort is different.
yes, I know, but for select they have two names: fast select and quick select. Fast select they use when we use MOM.
So that naming is changed. Yes, but quick sort is totally different. Where we are sorting, selecting we are
The
selecting
Quicksort
larger
was
number.
like the Tony Hoover's original work, like the inventor of Quicksort, right? The video is still there on YouTube, right? Clearly talks about not the
Yes.
original Quicksort, the way it was invented by Tony Hoover. Right? So, and then after that, there has been developments.
1965 in the paper only he has written about the MOM also actually, but it was not given until 1975 by another set of people. That's what professor was telling in the video.
So this research is going on. So maybe we will find any better algorithms in future.
Sir, what would be
That is
the
research.
statement for second one? Order n block. I forgot that create largest algorithm.
O of n.
First option is correct and third option is correct. Second is not.
No, how can we make second option correct? What should we do to make second option correct?
O of
Second option
n.
is not correct.
What can we write instead of
Sir,
n log
best
n?
case. What will be best case, sir?
No, actually, best case for the select. No, so select best case is
one.
n. No,
Sir,
not
this
order.
kth largest, sir. This kth largest. Worst case is one n. What will be best case?
Same n.
So, kth largest, suppose, okay.
Best case will also remain n because you need to perform partition process at least one.
Yes.
Okay.
Sir, next question.
Sir, how many slides are there, sir?
Sorry.
How many slides are there?
19.
5 are
Yeah,
five are remaining.
let's move on, sir. Yeah.
11, 15.
So this inversion are how many inversion are there?
Sir, your screen is not stuck in 13th.
1 second. Yeah, it is. So you can calculate this. I think this is easy.
Sir, could you do it very fast?
So 1, I don't know how this cursor is increased. 4, 3, 6, 2, 5. Okay, so 1, 2, 3, 4, 3, 5, 6. So 3, 4.
Sir, is there without crossing there is other way?
Or simply you can simply check. So by looking this first. Okay, so first is correct, coming on the correct place. It is not.
Yes, sir.
How many elements? Just see are coming after that.
So after 4 there are 2 elements, 3 and 2.
So it is creating 2 inversion.
And
then,
after 3 there
three,
are
only 1.
1.
Okay, it is creating 1. So 2 plus 1.
After 6,
okay, after
2.
6 there are 2. So 2. So 2 plus 1 plus 2.
2 is at
then
correct place.
So 5 is answer. Total 5.
Got it, sir.
Okay.
And if it is short one like this, then we can cross it and count the intersection words, right?
Yes. Okay, so just cross matching.
Sorry to interrupt here, sir. So where can I find the recording of the session? Actually, I have not joined before. I joined just now.
So live streaming is running.
No, sir. It's just recording.
No, I have. 1 second.
This link is showing only 10-second video. Yeah.
Oh, today is also long. Okay, so we are recording. So after, so we will upload this recording, or you can see the same recording on the calendar, also, after some time. Otherwise, we will upload this recording on the YouTube in maybe tomorrow morning.
So please, could you upload this as soon as possible? It will be.
Yeah, actually, it takes some time. Come on the mail. After that, it takes times of the upload, approximately 1 or 2 hours. So that time is required to upload. So maybe by tomorrow 10 a.m. you will find on the YouTube.
Okay, sir. Thank you.
Sir, show the question, please.
Where are the question?
A is 2, sir. A is 2.
So first, so the basic one, the D and C. Just talk about the D part.
Sir, B is also 2, sir.
So tell me the complexity for D.
Sir, D is like by
log n.
Is log n.
Log n. Okay, so D is 1. Okay, and C?
It's n
Just
square.
can you tell me which algorithm we found this recurrence relation?
Binary search.
No, C.
Or
Sir,
C is
C is
actually
worst
factorial.
case for quick sort.
Factorial.
C is
Yes.
quick sort, sir. This is n square. Worst
C
case
is the
of quick
worst case
sort.
of quick sort recurrence relation. So n square. Yeah. Otherwise, and B option is where we are
B
dividing
option
4
is
times and 4
second, I
N log
think.
n.
n log n.
So B will be n log n.
Yes.
B.
It's like a
Okay. So we are dividing n by
They are
4
all
and 4
equal,
child.
na? In each row it will be equal, so it will be n.
it's like a merge sort dividing into 4 parts, right?
Yeah. Correct. And after combining, you will get the same n by 4
Yeah.
into 4 n
Yeah.
at each
Yes.
level. So this will remain same. So n log n. And the first one is the where we are getting larger,
Less.
less or larger. Oh, n by 8
As
into
we
2.
go
Yeah, n by
lower,
4. Yeah, decreasing.
lower will be decreasing.
Yes,
So,
decreasing case. So big order of n.
order.
Okay. And next one is also similar to this. I think the same.
So the correct option for 15 is
Okay, so just D1. So D1 is okay. 1 second. C n square.
D is the right answer.
C4. D. No D.
D, last option.
D.
D is the right answer.
Last one, no?
Hmm. No. 1 second.
No.
Sir, it's B
Okay,
two.
okay.
B would be there,
Sir,
right?
B
Yeah,
option.
B is the correct.
Yeah.
Yeah. And this is the similar one. So n by 2 plus n. Okay, so this is not.
Screen got stuck, sir.
So this is not a binary search. This is you have seen in one
Complexity.
algorithm.
Order n complexity.
Select. No.
Sir, is this
What
type of
we are
mock?
having? We are finding one,
Quick select.
Quick select, yes, correct.
only one side
Fast
of
select.
the tree we are using. Only one side of the tree we will be using.
Sir, it is and its complexity will be n, sir.
N. Okay, this is the fast select recurrence relation, if you remember.
Kaya.
Quick select or fast select.
Not quick select. Quick select worst case is not the same.
Yes.
But fast select will this one. Okay, and next one is this 2t n by 2. This is simply merge sort. So I'm skipping this. This we have already discussed.
This
Done.
is increasing sequence.
Sir, what will be answer for this
N
one?
square.
N square.
Okay, we have discussed this example. Okay. I think all done.
Yes, sir. Thank you very much, sir.
Okay, all the best for quiz 2.
Thank you, sir.
Thank you, sir.
You're welcome.
Thank you, sir.
Okay, and after the quiz 2, we will just start the OPP preparation after discussing the week 9 content. Okay.
Week 10 also is released, sir.
Week 10 is released, but the OPP syllabus is still week 9. So start preparation of OPP exam. Okay.
Sir, OPP could be very tough for us, sir.
No.
Test, sir, we have to give for OPP that.
Sorry?
Pre-test we have to give.
Mock we will release, and also we will conduct the revision session by TA for the OPP preparation.
Sir, please release mock early, sir. I think 8 week has completed. 9 will come. So if you release before 10, we will discuss slowly. We will solve slowly every question.
Before after 1 week we will release.
Yes, sir. 10 to 15 question. If we will there, we will solve
10 to 15.
accordingly.
No, in the mock we have only 4 questions. But we will. I'll just discuss some areas where you need to more focus. Okay.
Yes, sir. Please provide that question that will be relevant, means somewhat.
Okay, okay.
But sir, for mock, do we have to give that? What do you say? Before giving that mock to some proctor,
SCT,
SCT, yes,
not required.
not required.